So, well, it's 2 o'clock. If you agree, I would start so that I'll leave the floor to Bruce in 5 minutes or maybe less. I just wanted to say a couple of things, and Raffaello, please intercept whenever you feel like it. I wanted to welcome everybody, and thanks for being here, and especially I wanted to thank the speakers. Now, the idea of this session on the boundaries of ABM is Raffaello's. Actually, his idea was to invite some of us in Varese. And then you might guess what happened back in the spring. So when the idea of the social simulation week came along, then we kind of talked about it, and we decided to do it like this. And I think it's a good way of substituting that. So this was going to be one of the workshops of the series on agent-based modeling of organizational behaviors, which is something that happens every year or every other year, depending on availabilities. So this was going to be the number 5, but of course it's kind of not. So it is, and it is not at the same time. So why we are talking about the boundaries of ABM. Now, the idea is basically to reverse the question that we usually ask ourselves, of what can ABM do for the rest of the social sciences? And the point here is, well, what can the rest of the social sciences do for ABM? And so it is a question of boundaries, and it's a question of some sort of external proximities of simulation modeling with various disciplines. The spirit of this is an unworkshop. So basically, we have given everybody the freedom to do whatever they want with the allotted time. So we don't quite know exactly what's going to happen. We hope we'll be surprised. But Raffaello and I might intervene every now and then to remind people of time, or to do something like that. But I mean, to kind of try and be more efficient. But you know, with Raffaello and myself, I'm not sure this is actually the case. But anyway, so I think we have a beautiful program. I'm looking forward to listening to what everybody has to say. We also have a few breaks here and there, so we will notify everybody when it is time to take 5. So I think I can stop here. So, and would thank Bruce for agreeing to introduce this this topic with the talk that, if I'm not wrong, it's called the philosophy of computational simulation. So thank you very much, and the floor is yours.
Hello, can everyone see the slides and hear me?
Yes, yes.
Yes, that's good. Okay, right. So I'll slightly change the title. Ha. So in this talk, I will raise 2 clusters of issues where agent-based modeling and social simulation philosophy interact, or may interact. But since philosophy is best done as a dialogue, I'll try and introduce each cluster of these 2, and then hopefully we'll have a period of questions, debate, and then another one until the time for this part is up. Philosophers generally do not have nice PowerPoint slides. If you go and listen to a philosophy talk, they either just drone on in a monotone, or they draw a really rough diagram, something like this. I'll be a bit neater than that. So here's the first issue, looking at some philosophical issues considered within a modeling landscape. Okay, so this gives you some idea really of how I think of modeling and some of the philosophical issues involved. So we have our intuitive understanding. This is what happens in our brains. We don't really understand how our brains do this, but it is definitely there. And the other sort of imponderable is the observed world. Infinitely simple or infinitely complex, depending on your point of view. It's often what we are ultimately concerned with. Now, in everyday life, we have a direct, almost direct interaction between the two. Our intuitive understanding propels our actions, and the observations come from the world and feeds into our intuitive understanding. But what's interesting from our point of view is all the modeling artifacts that lie between these, that in a sense we use to mediate between our understanding and the observed world. So for example, a bunch of text, an academic paper, or some verbal argument, as we are doing at the moment. Now, philosophy generally works like this. You use your brain to understand verbal argument and make verbal arguments, and you write texts and you read texts, and that is what philosophy is about. It may have some indirect application to the observed world, but on the whole, a lot of philosophy stays way up the top, up there. Now, so the question is, what about a simulation model? Simulation models can be used as a kind of philosophy, as a philosophical tool, just as a tool for thought. Just like text or verbal argument is a tool for thought, we can use simulation models. We can put our assumptions and mechanisms into these models and see the results, and that informs how we think. And how we think might then be applied in the observed world. Of course, we might then compare that model with another simulation model if we're having an argument. So we're sort of having an argument via simulation models. Now, there are some people who think that simulation models can only be used as a tool for thought. This is a very sort of rationalist point of view way of going about things. It's where a lot of constructivists using simulation models might be thinking, because you have a lot of freedom about your simulation models, since it only directly relates to your understanding and only then indirectly to the observed world by common sense interaction. The rigor in these simulation models comes obviously in checking and understanding your model completely and maybe comparing it with other models. Simulation models can also be used as a tool for communication and social learning. So if you have more than one person involved, they can communicate or negotiate by making a simulation model that is acceptable to both, or by critiquing simulation models. And participatory modeling does a lot of this sort of work with groups of people. And this is a very democratic approach. The people's intuitive understanding, the stakeholders' understanding goes directly into the simulation model, and in a sense they're driving that simulation model, they're determining it as an entity between themselves. And this can be very useful because the simulation model can provide a very concrete point of reference for discussions. So instead of talking about, I don't know, status in general, you say, okay, what's status in this model? And that can, it can shortcut a lot of philosophical quibbling and misunderstanding because you have a concrete example in front of you. But the question is, are they only useful as a tool for thought or communication? There are some people in our community who definitely think the answer to this is yes, really. You can only, it's only really useful as a way of thinking about stuff. But I think there's another possibility, and that is when we mediate with another kind of model called data, and we compare these in a chain. So there's some sort of measurement process, extracting data, making a data model of observations, perceptions of the real world. We check the model against data in some way, and then we think and argue about the simulation models, the result. And broadly, I would claim that part of doing science means staging the process between observed world and our intuitive understanding into smaller checkable steps. So here we can check the measurement, we can check the model against data, and in a sense, the top layer, we can discuss and critique the interpretation of the simulation models. Of course, if you have two simulation models, you have the question, how do you select the best model? By which appeals most to our theories or reason? One often suspects that in a lot of the literature, it is the easy to understand models, the cognitively appealing models that appeal to people the most. But maybe another way, or which explains the data the best or the most, a more empiricist point of view of judging models. Some philosophers of science see models as mediating between our intuitive understanding and the observed world, and wouldn't say that any model is better than any other model. So all that work we put into producing a better model is useless. All we do is we get a different kind of model at the end of it. So this is a sort of more evolutionary picture, evolutionary epistemology of simulation models and how the selection factors by which different simulation models might evolve. From my point of view, one of the most important things about simulation models is that they are a formal object. That is, you can replicate and change simulation models without error, because they're not based on an intuitive understanding and subtle assumptions, but you can actually look at the code, produce the code again, check the code, and then compare the code in different ways, discuss the code. So the real use of formal systems for understanding the world is not that it magically sort of magically corresponds to the world, as some people believe about maths, but just because it's a very flexible system and we can develop new models until we get one that does fit. In recent work, different ways of arranging models have appeared. So layering models. So in some work I did in a long project, we had some data from the observed world and we built complicated descriptive simulation models, which also used theories, but theories that had some empirical grounding. From this really complicated simulation model that social scientists built with me, we then passed this to physicists who then made a more abstract simulation model that docked to the descriptive simulation model to see which bits of the simulation model were essential and which they thought were not essential. They then did some analytical maths models of the abstract simulation model and got some understanding from that. So here we're taking this layering of the stages between the observed world and intuitive understanding even further. We're not doing it in 3 stages, we're doing it in many stages. One of the advantages of this, it separates out the representational steps and the lower levels from the abstraction and simplification steps. Normally, when we're modeling, we do a mixture of representation and abstraction all at the same time. And this separates these processes out. And it allowed physicists and social scientists to collaborate in this case. Oh, that's better. One way of using qualitative data empirically the other intuitive understanding is someone you are modeling. They are not a peer. They're not a peer of you, in a sense, collaborating and controlling the model, but they're someone being modeled. And you might take interviews with those people in terms of qualitative data. You might analyze those, which you might use to build simulation model. Often theories are involved in the analysis of the qualitative data and other data to build that simulation model. Notice how this pattern of use of models is very different from the participatory picture we had before. And although people often get confused because they both involve qualitative intuitive understanding in different ways, they're used in very, very different ways and for very different purposes. So my conclusions to this part before we open it up to any discussion. Yes, I have a bias towards thinking of everything in terms of models and how they relate. Very unsurprising. There are usually a host of such models involved in any one project, and not all of these models are explicit. Some of them tend to be implicit. It's good to be very clear about the purpose and role of each model in this constellation, and preferably a different model for each purpose, rather than trying to conflate purposes all into one model. All in all, we're trying to leverage some understanding of complex phenomena using these models, and that may involve new constellations of models, layering, use of qualitative data, etc. like that. So I'm going to stop sharing, and I hope people might have some questions, points of view.
Thank you very much. This leaves a lot of room for discussion. So
it does. I'm hoping I don't have to say anything else.
So anybody, please use the
or wave your hands. Christopher, yes.
Tool. Yeah.
Okay, rather than type something in chat, I shall jump straight in there.
Philosophical of you.
Okay, well, we've seen a couple of circles with intuitive understanding written in them, but overall there's not much of an impression of modeling being a social activity or part of a social activity. I like to think that knowledge isn't really in the individual scientist, it's a property of a social network of scientists. This is particularly obvious when you mix with qualitative social scientists, and they'll have done 3 case studies, yes, but they'll have done them with the eyes and the terminology brought about by being part of a community. They'll go to conferences and have enter slanging matches as they try to negotiate membership of the social science gang there. So
yes.
So yes, it's very much a social activity, and maybe your bubble diagrams don't really get that across.
Yeah. I tried putting lots of people as well as the different levels on one diagram, and it was a mess. So I simplified them out because it became, it just looked like foam. Some of the processes, I mean, one of the slides I had 2 intuitive understandings, obviously by different people, but some of these some of this interaction is implicit. When you're making an argument, a verbal argument, as we're doing at the moment, it's implied that the purpose of that is between people. I don't usually argue with myself in the bath because it's too easy. I win all the time. Secondly, the text, the point of externalizing thought and putting it in a text is usually social. You write a paper. It's an object that's a fixed object that people can critique, look at, understand, question. And in a sense, philosophy made a big jump when it moved just from purely oral, and actually people wrote them down. so that then people can then go back and look at the same text and argue about them. So you're quite right. In essence, I just agree with you. I was just limited by my diagrams.
Okay.
Okay, thanks. I'm scrolling up and down, but I can't see hands. So perhaps
people just jump in, turn on your mic and talk if you want to say something.
Well, I think I'll ask you something before.
Yes.
Because you, at one point you said, well, simulations can be used as tools for philosophy. And now
yes.
My question is, well, philosophy is a very broad subject. And I was wondering, are you referring in particular to those type of speculations about science, or do you think that it can be used for aesthetics as well as for ethics, or is there a boundary there where we go?
It's evolving. Philosophical papers in mainline philosophical journals are starting to appear with agent-based models over the last few years, and workshops are starting to happen. They are often concerned with maybe social dilemma issues, for example, or a bit about how science works, the philosophy of science. So those are the areas I'm aware of. There are a few ones about ethics. There was a paper a while ago called Artificial Ethics, a book a while ago called Artificial Ethics, nice book. So it's starting to appear. Obviously, like all subjects, agent-based models sort of percolates at different speeds into different subjects. It often requires someone who's established into that field to discover agent-based modeling, and then it becomes all right for everyone else to then start using it. So yeah, I think it might be better for some things than others. Obviously, we're trying to simulate the emergence of meaning or something really difficult like that. I'm not sure we're up to that yet with simulations and how to implement meaning other than in very semantically thin ways. You know, you can put in semantic nets, you can do all sorts of stuff. We have no idea whether that's right for humans. It's hard. So some areas are going to be easier than others, certainly. Any other thoughts or questions or just comments?
Yeah, I'll just add to what you said there.
Yes.
Have a few friends in philosophy in Cambridge University, and know that there's. I was pleasantly surprised to discover that they were. They've got this subject called social epistemology, and in which they were supposedly doing simulation models of science, and I'd.
The label social epistemology says it all, doesn't it, about their viewpoint?
Yeah, well,
forget the objective. Let's have intersubjective. Yes.
So if you come to this field having maybe followed Flaminio's Peary project, especially in the early days when they had a lot of agent-based models of scientific discovery, of how that relates to publishing and so on. And then you come and see what gets you published in a philosophy journal, and it's like, whoa, this is really crude, and whoa, that's a very naive view of how scientists actually work, and so on. So, so I mean, if anybody's interested and wants to make an impact, can go over from sort of the Peary stuff.
You somehow have to translate it. But you have to somehow translate it into philosophical language to be acceptable. Yeah, so it'd be better to team up with a philosopher. But yes,
so you have to cite their people. As we're anywhere, yes, you have to negotiate membership of the group, of the network.
I was at a workshop on using agent-based models in philosophy, and they were making all the classic mistakes that all of us made early on, and lack of validation and projecting onto models and seeing the world through your model and deceiving yourself totally about the certainty of your conclusions. Anyway, Stephen.
Yeah, you touched on my question actually. My question is about validations. Because when I look at when I listen to you, most of the time, the models that I do is based on a measurement process. So the validation is by comparing it with empirical data. But when you say that using simulation models as a tool for thought from our intuitive understanding without any data, it raises a question to me. So is there such thing as valid model here, right? Because it's
No.
So
it's only, you could compare it to other models, you could compare it to other theories, you could compare it to other ideas. So there's a sort of coherency idea,
I see.
But no validation. No.
Yeah, so when people ask how you validate your model, it's a wrong question to ask, isn't it? Or
yes,
okay.
You make the ideal non-philosopher, Stephen, I'm proud to say.
Thank you. Because I need to talk to you more.
Good.
Maybe just a random point, if I can chime in here. Sorry, hi everyone.
Patrick, then Martin, yes. Yes, Patrick, then Martin, yes.
Actually, right now, parallel to the Social Simulation Week, there's the Environmental Modeling and Software Conference going on. And there was a paper published there where they basically tried to find all the models that would reproduce a particular data series, right? So if you think about this in the context of like validating a model, right? Like you make a model and you check it against a data series. And they found that essentially there's an infinite amount of models that can produce any given data series.
Sure.
Right. So I think that does really challenge the idea of like, oh, I've made a model and it fits the data, therefore it's valid.
Yes,
or useful, or
that's right. Yeah.
Anything,
most models are constrained in their specification by some plausibility rules that limit that result. You're not usually totally free to make any kind of model to fit some data. But yes, just fitting data has to be only part of the equation, and it certainly vividly illustrates for that. Yeah. Martin had a point next.
Yeah, I have a tiny little nitty-gritty question, which is a little bit nonsense, perhaps.
True philosopher.
Yeah, because you carefully said about observed data, and on the one hand, and not the world, so to say, you carefully avoided to speak about the world, so to say.
Well, I talked about phenomena, yes, etc., and the data is derived by some measurement process, perception process from the world, from this phenomena.
And then you had, on the other hand, this empirical, intuitive understanding, and the error with representation in between it. Certainly, that's all issues that are heatedly debated in philosophy. And my basic, simple question is, because when you say you have observed data and intuitive understanding, which is also something about understanding of the world. So basically, what's exactly the difference between intuitive understanding and observed data?
In practice, there's a lot of difference. You are right in the sense that theories and ideas will be intimately involved in the process of deriving that data. There's the old measurement regression. So to do measurement, you need a good theory. To go do theory, you need a good measurement. You go back in time. But over time, it is possible to slowly bootstrap more reliability, more objectivity into it, even though it's this sort of infinite process, as science has shown. We have more and more accurate and reliable measure in some fields. In other fields, psychology, We have a huge measurement crisis, a replication crisis, and we've obviously pretty well failed to measure a lot of stuff about human beings in any reliable way at all. But in some fields, obviously temperature and stuff like that, it has been successful, and the bootstrap process is involved. But yes, I mean, again, if I put in all the possible blobs and arrows, you know, it would just be a mess. But you're right. Yes. I mean, I'm summarizing here, and of course, you could go into each of these processes and look at and go down another level and look at the assumptions behind them. But in practice, you know, we have a lot of processes that derive data from the world. You know, what we click on in ads or something like that. And that's quite different from our intuitive understanding of the world.
If
yes, there are philosophical hard difficulties.
Yeah.
Bogner, you want to say something?
Yes, please. Because very often I see that the idea that if you are capable of replicating data with your model, you're on the right track and develop a valid model. But it neglects the idea that data are just originating from one manifestation of history. And we should be very aware that in particular in complex systems that are in a more turbulent stage, that the data could have been completely different. So what I usually think is important to keep in mind, that a model should be capable in principle of replicating the data, but a model should also be capable of helping you in identifying possible alternative manifestations.
Yeah. There's a big contrast.
And that makes it very nasty.
Yeah. There's a big contrast between physics, where there's a whole layer of people who are just inventing new ways of measuring things reliably, and social science, where there's one or two postdocs doing that, and then there's all these hundreds of people inventing theories. It's sort of top heavy. And in social science, somehow we haven't got the importance and right. Are there people out there checking the kinds of data, what I call data hounds? I would love to have an office full of data hounds I could send off to find and check data for me. It would be wonderful. Usually you're left doing it yourself. But you're right, it's absolutely important, and there are very subtle assumptions behind all sorts of data that comes in. Completely right. We've got a chance for one more question before we go on to the next bit.
Can I jump in then?
Yes, who's this?
Stefan.
Stefan again.
No, I've just the one that mentioned about fitting the model, fitting the data is not validation. It is part of validation, but it's not. What about the model has to be able to explain what we want to observe, right? So the explanatory power of a model. What do you think about how it fits into your framework here, Bruce? Because you have very nice framework here.
So explanation is obviously only one possible use for a model. It's the one that us more empirically minded people using agent-based model concentrate on, because A, it's possible, and B, it's quite a good tool because you can put in the processes into the model that you want the explanation to be in terms of. And so you actually, unlike sort of economics or something where you don't get an explanation out of it. And so, yes, I mean, again, that's quite an involved process, which I've simplified hugely here. In the modeling purposes paper, there's more discussion about explanation and how we might use that.
Oh, okay.
For the person building up, context in the chat, that's a big topic which I've written lots about. I will just write you a link to some of the papers, and maybe you can email me, Vahid. Thank you. Okay, I'm going to go on to my second part because we've used up the majority of the time I can find. There we go. Okay. Can I start further down? Would help, wouldn't it? There we go. Okay, so the second part I'm going to talk about is not agent-based modeling as a knowledge integration tool. And here I want to really thank Gajary Polhill, who've organized a couple of workshops on this topic. And we've written a first sort of conference paper together, a bunch of us. So where does one get integration? Where do you go to for integration? Obviously, individuals can use their intuitive understanding. As Christopher pointed out, groups can come to integration as a result of discussion. Philosophy has often been an integrative topic where you're trying to integrate different sources of knowledge and put them together. From the 70s, there's systems thinking and second order cybernetics, abstract maths, for example, system dynamics models, artificial intelligence in the 90s. When I went to workshops in the 90s and AI, you got all sorts of different people there, social simulators, social scientists, philosophers, computer scientists, all sorts of people there. It was integrating them. And now agent-based simulation. We are very lucky in this, this conference that we get all sorts of people coming to the conference from very, very different backgrounds. Agent-based models can use all sorts of different data and sources, time series, distributions derived from surveys, qualitative counts, analyses of priorities from games, the NETS framework, social network data, behavioral theories, other models, policies, geographical data scenarios. I didn't list them all, there's just a lot of them. However, what is meant by knowledge integration is often not clear. When you get the integrated knowledge, do you get new knowledge, or is it just somehow a collection of all the knowledge you put in? If so, what is this new knowledge for? How can we check that the integration was consistent? What if very different assumptions were behind the different elements? So I'm being very critical, following my colleague Scott Moss, on people who use Likert scales. That is, you get a survey and you have to put a number from 0 to 9 and how much you agree with some statement or other, and then they get numbers, and then they do things like form averages of them. And that builds in the assumption that the intersubjective scales are somehow compatible. What the scale of one person answering them is somehow compatible with another, and you just can't do that. Those are ordinal numbers. They're not cardinal numbers. Just a simple example. Do you just get the result? Is the result just a sophisticated fudge? Can the process actually be critiqued or replicated by others? Can the integration ever be maintained in the future? So it's a really problematic area. The plan is vague, often in a project. We'll use some participatory methods, ABM, and build up a more complete, accurate picture of what the actors do and how they interact. We'll check this with a bit more participation and eyeballing the plausibility of the results model to assess different policies, and so be able to recommend the best. Here's a typical EU project. I'm sure not Vonda's, but most of them. Often knowledge is left as an afterthought. There's not enough mapping and analysis of the elements that will go into the integration, and this is done informally. Often it's dumped on some new postdoc, or it's just the outcome of a discussion. It's often used to the left of the famous work package 5. That's the work package for integration that was just added in as an afterthought at the end of the grant writing process. Not enough analytical rigor goes into this process, not enough verification of each kind of integration step as it happens, often none or very thin validation of the integration, resulting in what two authors called integronsters, which is the monster that appears when you just stick a whole lot of models together. The philosophy of knowledge is exactly about the different natures of knowledge, the limitations and assumptions of each kind, whether they can simply join them together, how they might be used, interpreted, issues of context dependency, level, etc. to help make the steps more explicable and testable, but philosophy is where it's had. So we're often called in to help integrate knowledge, but it's not clearly defined and often far, far too ambitious. Knowledge integration is very hard and can't be left as an afterthought. Philosophy and agent-based modeling need some work to integrate them first, so we can actually look at how they might work together. But agent-based modeling is the most promising formal approach to help make this task more rigorous. Okay, some reference, which I'm not going to go into. And we have a few minutes, not many, for a final comment. I can foresee the future social simulation week becoming knowledge integration week. Agent-based modeling is just a tool. It's just one approach to doing that, yeah? I feel my job is often as a knowledge integrator. I happen to be good at one particular tool. Any comments? We're almost out of time, 3 minutes, so there's only time for a...
Maybe I'll
yes,
ask you
Davide.
a question, because all the, not all of them, but most of the tools that you mentioned, like systems theory and system dynamics, etc., they kind of all failed for one reason or another. So
including philosophy?
Well, ask Nietzsche, I guess. But so I guess my question is, what is the risk that we are facing as a knowledge integrator, not to make kind of similar mistakes? Because, for example, perhaps systems theory was overconfident that everybody could understand those set of differential equations the same way, and it just didn't happen. So do you think we are kind of making the same mistakes, or we face the risk of making similar mistakes?
The technique doesn't face a risk. Once a technique is out of the box, it's there, and people will use it for all sorts of stuff. It's too attractive, just like animated system dynamic models are attractive. They're not going to be put back in the box. But as a sort of topic area, social simulation is very odd, because what we have in common is a tool, and yet we're modeling very, very different stuff, all of us. And it's not clear that there's enough to hold us together in terms of just we happen to use the same tool. Are we going to be like statistics? We're going to be called in when a statistician is used. It tends not to be the case. Most of the people here have a foot firmly in certain topic areas. They're not complete generalists. And they have that knowledge of their area is important in informing their agent-based modeling. You just can't come in as a newcomer into, say, I don't know, organizational dynamics, and then expect to make a good model. You'll just make so many basic mistakes, or for that matter, SIR models of diseases. You'll just not do that. I think some of the difficulties are that agent-based modeling is so attractive on the surface. The idea we can put everything into the model, the idea that we can animate it so you can interpret it in social terms very easily, it's very attractive. There's an easy, simplistic mapping from the real world to the model. One person is one agent, one interaction is one interaction, etc. So it's easier to interpret the mathematics, and all of this makes it very attractive on the surface. And I'm sure I'm just waiting for some advisor in government, probably Dominic Cummings, to apply an agent-based model to some area in a simplistic way and make big policy decisions and screw us all up, and agent-based modeling. So I'm very frightened that that might happen, and we might fail in a similar way. I think the potential is there for agent-based modeling, but the jury is still out. Notice we've run out of time, so it's up to you, Davide.
Yeah, I think the time, unless there is a very quick final point, I think we'll move to the 5 minutes break. So we reconvene at 2:50.
Great.
Thank you very much. Thank you very much. So Jens, the floor is yours.
Yeah, thanks, Davide, and hello, everyone. I hope, can you hear me?
Yes.
Yeah.
Excellent, excellent. I hope you can hear me and not my upstairs neighbor who's decided that a Friday afternoon is the time to start a heavy bass music party. So I'm going to talk a bit about the importance of being human in agent-based modeling. And this is something that is really close to my heart, especially because I've got a background in cognitive psychology and in the theory of persuasion. And what I want to show just as an example in these like 5-6 minutes that I have to present this before I turn the table to Davide is just one example of some work that I've been doing with, amongst other people who are present here, Ernesto Carella and Nicolas Payet. I hope they don't mind me giving them a shout out, and they're wonderful people. So this is some work that we've been doing specifically in trying to model phishing effort using an agent-based model. So we were interested in figuring out how environmental sustainable and sustainability could be achieved or sort of modeled through an agent-based model. So the last couple of years, we've been using a model called the Poseidon Model, which Ernesto has done the bulk of the work in coding it, and Nick as well. But this is a lot of Ernesto and Nick's coding work. And it basically consists of these sort of 5 components. So you've got an environment with the ocean conditions and the coastlines. You've got an ocean ecology model, which is spatial, so like the fish in the ocean. You've got obviously a fishing fleet trying to figure out where the fish are and what to do next, where should they go next, like tomorrow to fish, to fish, what gear should they use and stuff. And then these fishers are influenced by external markets and by the policy in which they operate. And my job largely has been to try and figure out how we can conceptualize this little box, so the fishing fleet in particular. And we've been doing this in a variety of different ways. And one particular slice of the project that I just wanted to talk to you today about to exemplify how one could go about more sort of ethnographically starting to implement the human within the agent-based model is some work that we've been doing in Indonesia. So for us, it was really important to talk to the fishers. But before going into it, I just want to show you 2 very brief illustrations of what Poseidon can do. And in the bottom here, you've got like the main paper where we present Poseidon for the first time. But since then, we've been doing stuff on calibration and validation. We've been testing various different models and expanding Poseidon quite a bit. But 2 sort of fundamental uses of Poseidon. One is to simulate fishing effort. So in this case, I hope you can see my cursor here. The green bits are the beach or the land, and the blue bits are the ocean. Red bits indicate fishing pressure. And here you have a gray bit in the middle, which indicates a marine protected area. So in this case, the agents learn how to fish the line around the marine protected area, which is an expected aggregate outcome that you would find often when MPAs are being introduced. So one sort of component is to replicate both individual and collective fishing effort, or sort of not replicate necessarily, but show different strategies. And the other is to test and find interventions to manage this this complex human environment system. So around this model of Poseidon, we wrap a meta model of a Bayesian optimizer, which can test and find policies. So in this case, the optimizer is trying to figure out where to place a marine protected area. And there's a nice Pareto optimality where there's small boats and large boats in this context. And in this case, you see, like, if you place the MPA here, which the computer has found, then the small boats do quite well, and there's a large total catch in general. So the large boats do quite well. Whereas over here, the small boats do really well, but the large boats go bankrupt. So we were really interested in trying to figure out how we're going to approximate these human beings in the fishery model. And we're applying the Poseidon model to Indonesia. So I went for a month and lived in a variety of ports in Indonesia and just spoke to people to try and get a sense of their lives, what was important to them, and what we could build in to the model as behavioral assumptions, either specifically about choosing some place to go, or on the information level of figuring out how they learn about the environment and stuff. And in particular, we were interested in going beyond as well, just the economics of the concerns of like, is this fish more valuable, or is that trip more valuable? And how do I do it with rising and falling gas prices? Do I go further or closer to shore? And just to illustrate some of the findings that we uncovered when we were out there, we found that obviously, no surprise, but fishers consider other factors other than income. So for instance, a lot of the fishers in Indonesia are Muslim, and they consider not fishing during Ramadan as a cultural norm. So even though they know that they're going to lose out some money, they're going to decide to not fish during Ramadan because that's important to them. It similarly as well, a desire to maintain a good personal reputation within a fishery as well, or within the port. And we found, like, for instance, differences between ports. So commercial fishers are more focused on incomes, whereas small scale are more focused on the personal reputations and the communal norms and cultural norms and stuff like that. Further, we found that some of the social aspects are critical and very culturally relevant. So for instance, information sharing practices really differed a lot from port to port. So in some ports, almost all fishers would share with each other where they went, what they caught, and so on and so forth. Whereas in other ports, no one would share. And obviously, when you conceptualize the way in which people learn and then make use of that information to make a decision, whether or not people share information within the port is critical. Same thing, imitating someone else. So like going to someone else's plot, like if I see Davide fishing over here, and then I go over the next day and fish on his turf, if you will. Some places that's culturally penalized, whereas in other places it's not. Same thing, knowledge of other fishers, what they do, what they earn, is very port specific. There's a large cultural component as well to this. There's other factors, obviously, such as recency of experience or the memory of fishing in various places, and the income satisfaction economically. What they considered a satisfactory income was both absolute, so I need to earn above X amount of money, but it was equally social for most of the fishers. So even if they were above their absolute threshold, if the guy next door to them started earning a hell of a lot more money for the same amount of effort, they would consider their income to be unsatisfactory. So there's indications that various fisher archetypes may exist. So like small, like commercial, large commercial vessels versus small subsistence vessels and stuff like that. And we could use these ethnographic findings to try and populate models with fishers who are what I would consider more human within this model. So it suggests that there's psychologically heterogeneous fleets, not just economic and demographic considerations, but also psychological considerations. And these have real and sort of potentially large impacts on how they can adapt. So if we want to understand how the fishers may adapt to these contextual changes in economic, biological, policy, or whatever, we kind of have to understand the psychology of their behavior as well. Now, I completely agree with all the problems within the field of psychology of replication, of overfitting, of just so sort of stories and all of this. But this is more to tell a story of why I think it's so important to consider not just the humans or the agents within the ABM as abstract constructs, but also maybe engaging with some ethnographic models and ways of trying to conceptualize people. So just to round off, before I hand it over to Davide, we implemented just like some of the very basic findings within Poseidon. So we showed, for instance, if you have a cultural taboo area down here that's forever, for whatever reason, is a taboo to go fishing for half a year. You see, like in the beginning, everyone, and this is a marine protected area, in the beginning, everyone sort of holds away and like fishes close to port. Then when the taboo is lifted, because fishing is still pretty good, only a few go down. Then the taboo comes back. They learn to go further afield and start fishing on the other side. And as soon as the second year taboo is lifted, they really start congregating around here in the taboo area because there's lots of fish. And in the end, fishing becomes so sparse that they start breaking the law and going into the marine protected area because of economic satisfaction considerations. So that was just a brief little story of why I think really considering the importance of being human is critical, because it influences how they adapt to the changes in the environment, both temporally and in terms of policy, like or economic changes, as well as trying to understand like some more sophisticated beyond just economic considerations, what makes a person tick within an agent-based model. So Davide, I will throw it over to you, and I'm sorry if I've gone 2 minutes over the time.
All right, thank you very much, Jens. Thanks. Okay, so I'm going to share my screen now, and I think it is this one that I would like to. Okay, so can you all see this? Can you see it? Yeah, okay, yeah. Good. I'm going to talk about bounded rationality, but not really. So I'll just move to it so that you see what I mean. Now, part 2 is about the questions that I mentioned before, so I'm not going to cover that right now. I'm going to present 2 cases, basically. So first of all, just to give you an idea of my work, I study organizational cognition, so I am within the field of management and organizational research, but within that field I'm an odd person because I do ABMs. The question here that I'm trying to ask to myself, but also to you if you want, is what it is that organizational cognition has to offer to agent-based modeling. And that's interesting because I usually ask the other question, you know, what it is that ABM has to offer to management, to organizational behavior, or understudy teams, or public administration, etc. So, but this question is somehow interesting because in the following few minutes, I'll try to outline how a particular perspective, which is the embodied and distributed cognition perspective, could offer when we think about agents cognition. Now it's a big word, agent cognition, but let's leave it like that for now. So basically the question about bounded rationality, it is not how to implement it in general, but it is basically a question about how these bounds of rationality work. So I'm going to give you 2 examples from 2 models. One is the IOP model, a model of intra-organizational plasticity. Basically, I think perhaps it is a simple model, but it is a model of an organization that faces times of crisis. So the tasks that all the employees have to perform increase at different rates and at different times. So the question of the model is how it is that they use resources, including other people from their team, more effectively. So what are the cognitive strategies that emerge, to use a word that is very familiar to ABM modelers, in these cases? And by using these 2 extended and embodied inactive cognition, there are 2 strategies. Now, maybe I should mention briefly what the plethora of different perceptions in distributed embodied cognition mean. And it basically means that the cognition doesn't happen just in the school, but it is distributed over an interplay between external resources, other people, tools, artifacts, natural resources, and the brain. So, and it is this interplay that I have been trying to model. So one strategy that emerged from this first model was a cognitive differentiation strategy. So when basically the number of tasks to perform increase to moderate to high level, the agents, the most successful agents do not stick to the same resource. But the best strategy would be to change resources. And this is kind of strange because I modeled the agent the other way. So it is meaning that I have been using an extended cognition perspective, and reliability and accessibility of resources is key in that perspective. And yet those that were performing...
Davide?
Yes.
Davide? Sorry.
Yeah.
Oh, sorry. Yeah, I think someone else is about to say the same thing. The slides are not moving for the rest of us.
Oh, okay. Okay.
Sorry, I don't know if this was what the other person was about to say.
That was exactly what the other person was about to say.
Thank you.
Sorry,
Thank you for saying that.
It's a nice convergence of like amount of time that passes before someone pipes up, and apparently we have the same threshold.
But now can you see it now?
Yes.
Yes.
Okay, maybe I'll leave it like this, and if you can't see it, and I don't go full screen, is that all right? If I move now, you can see it that it's moving.
Yes.
Great. Thanks. Yeah, sometimes it happens, but go. Okay, so but you were with me with the strategies, right? So the first strategy is this cognitive differentiation strategy, where instead of sticking with the same resource, they move and use different resources. The second strategy instead is the most successful strategy when the tasks become extremely high, so they increase exponentially in the system, is a concentration strategy. So it apparently those that stick with their teams mainly, so that use pro-social interactions more often, are capable of solving the most difficult tasks. Now that's one model. The other model is a model about information. And it is about non-functional information. In this model, what I tried to do is to ask the question, okay, what happens with the information that it is apparently not related to the task at hand? It's still within an organization, still within a team, still modeling pro-social interaction. So teams that deal with a particular task they need to solve. So this non-functional information is, it can be either dysfunctional or completely irrelevant or pseudo functional. It doesn't matter here. What matters is that what I found is that in the model, there seems to be not a significant difference between those agents that use functional information and those agents that use non-functional information in the amount, in the total amount of tasks that the system, the organization could perform. So it seems that this through doing thinking, the thinking through using a particular tool is what was happening in this model. So the final remarks here are that perhaps not all bounded rationality is born equal. And what I mean with that is that perhaps we need to start asking questions about what are these bounds, whether they are stable, whether they are fixed, and whether they are stable or they are moving bounds, and if they move, how it is that they exactly move. So what happens around them? And then, of course, this leads to questioning the standard assumptions, like a question that in a recent review of cognition applied to organizations, I realized that nobody ever questions what information is. And for example, if you take a more clear stand on what cognition means and how agents or people are capable of making sense of the world around them, well, that's a question that you can't avoid. The final thought is that perhaps ABM is slightly richer as a tool of theory development as we kind of thought initially. That's my part. Thank you very much for listening. I think we now open up to questions. I should stop sharing my screen. You can either speak up or raise a hand. I think I could see it, or otherwise we'll ask you questions.
How would you recommend that people deal with representing information in a model or something?
Well, that's a huge question, and I would say, well, it depends on what it is that they're modeling. I mean, as you said before, that we come all from different fields, and I think that we have different needs for our models. But I think what a key point of looking at information, it would be that perhaps it is difficult to think of it as an objective property of an element. It is always something that needs to make sense of.
Yeah.
So,
They need some semantics of some kind.
So perhaps that would be my advice, that don't treat it as an objective property of the agent, the system, the etc.
And especially not a number. How much information?
Well, it depends as well. Again, like, so one of the other models that I've been working on the agent-based modeling side is a model of echo chamber formation, which is like people trying to search for what they believe is true within the bounds of a probability estimate. So in that case, like, it's more about beliefs rather than information, but they can seek out quote unquote information from other agents within that system of what they believe. So it's very nebulous. Of like, information is a really nebulous word, I find. So I think Cesar Garcia Diaz, did you have your hand up? Maybe not. Sorry.
Yes. Davide, thank you very much for the presentation. I wanted to ask you about knowledge transfer. So there is a huge literature on in terms of modeling aspects of knowledge. Now that you touch this topic of cognition, how do you see this related to knowledge itself and this difference between information transfer and knowledge transfer?
Thank you very much, Cesar. That's an intriguing question. And the field of organizational cognition deals with knowledge and learning quite a lot, but not with and information as a process of transferring some data in between individuals. So, well, I would personally treat them very differently, meaning that information is, as Jens was saying, it's not clear what it is exactly. Is it just data, or is it something that needs to be experienced somehow? Whereas knowledge, perhaps it has also an objective type of element, but still, I would stick to Maturana and Varela's tree of knowledge in saying that there is no such a thing as knowledge unless there is somebody who knows. So I would say that this seemingly objective type of mirror just falls down because that's just impossible. So I would say that to some extent, I would still consider it as a subjective type of element. As far as information, perhaps it is a part of that. So it is how there's a lot of literature on knowledge transfer or knowledge storage or etc. And information seems to be a part of that. But I would not reduce the two one on the other, for example, and vice versa, if that was the question.
Yeah, thank you.
Shavas, did you have a question?
Yes, maybe to Davide. Thanks a lot for the presentation. I'm just a little bit naive and also curious about the research on bounded rationality. Because if we kind of roll back to the story from like Herbert Simon or James March, and I cannot really find a lot of literature like really trying to analyze or dig into bounded rationality or apply it in empirical contexts or settings. And are there some like some streams of literature for that, or there is a reason that are not there are not many people really going after it?
Thanks a lot for the question. Well, this has been a long quest within people who approach bounded rationality, and there is a kind of a famous article published in 2004, I think, by Nikolai Voss about bounded rationality. That, I mean, the title was something like "Much Cited and Little Used." Kind of, and so it was a review of the literature to highlight exactly this point. You know, everybody cites it, but when it comes at applying it, actually, well, we're not sure. In fact, we're not talking about a theory of bounded rationality, because we're not sure if it exists or not. But I mean, going to your point of the literature, there have been several attempts at modeling bounded rationality. I think there was a book by a mathematician, I can't remember his name exactly, but it's a pretty famous on models of bounded rationality with all the different ways in which you can mathematically put down bounded rationality. And then, of course, the most famous, perhaps, exemplifications of bounded rationality come from Kahneman and Tversky and Giger and Selten, of course. And more recently, I think also Taylor and Sunstein and all the nudge people. So that the literature has gone empirical, quite straight, and the models, I think and the models, I think, come that way. But I think, Jens, I think unless you have something to add, I would ask the questions now.
Yeah, I'll just quickly add like 30 seconds on this, or a minute. So like one of the challenges I think often in bounded rationality is that it's often defined as like the incompletion of, like, the not having complete information, or the not having complete time to compute everything. But that's kind of like drawing in the negative space, as in like, oh, these are the things that this agent is not, but not all the things that it should do. So like it can be like anything almost can be framed as a bounded rationality if it has some kind of limitation on it in some kind of a way, either through information deficits or time deficits to compute the right answer or something. So it becomes difficult to sort of say like, oh, that's a bounded rationality model. I think that might be part of the problem of applying it. And it's a nice segue actually, because Davide and I, part of what we wanted to do with this session as well is to maybe pose some questions to the community, especially on this topic of bounded rationality. So I don't know, Davide, do you want to?
I'll share the screen and we can talk about this together, perhaps. So this would be, I'm assuming you can now see my screen. So, all right, good. So this is just a reminder of a definition. So I'll just read it. Rationality is bounded when it falls short of omniscience, and the failure of omniscience are largely failures of knowing all the alternatives, uncertainty about relevant exogenous events, and inability to calculate consequences. So basically 2 bounds, internal and...
In other ways, the temerity of not modeling gods.
Yeah. And the 2 here, Simon and Newell playing chess, because that was their example of the decision maker, or actually general problem solver. So we are, as modelers, we use bounded rationality quite a lot. I would like to cite the introduction of the handbook by Bruce Edmonds and Ruth Meyer. It's a kind of a tribute to Simon. So there is a very tight link over there. And let me skip the rest and go to questions. So first question we have is about contribution. And the question is whether there is a contribution of the ABM to the study of cognition and bounded rationality within this, and vice versa. What is the contribution of the theory of cognition to ABM? So what have these to offer to ABMs? Second question, it has 2 parts. Since bounded rationality has a very old-fashioned I want to say epistemology, but let's I've said it, but let's assume that you haven't heard it. So it has a very old set of assumptions that carries over. So if we say that we model bounded rationality, then are we kind of promoting an old-fashioned view of the mind with a technologically advanced tool? That's a question. Second is, so since we have other approaches, ecological and positive approaches to psychology of decision making that have been advanced in the past decades. So how do we exactly introduce agents that can be defined that way in ABMs? That was our second question, split into two. And then number three is beyond economics. So what are the characteristics beyond economics and beyond utility that are challenges when you model cognitively informed agents in agent-based modeling? Here are some examples: memory, learning, information sharing. What is it that makes modeling these things difficult? I think we have 8 minutes.
And one of the things that that really sort of, at least for me, is a big challenge, because I come from sort of behavioral sciences and cognitive psychology, and there's been a large push, for instance, by, as Davide mentioned, like Kahneman and Tversky and like a lot of people, to sort of identify empirically functions that are non-rational or sort of non-optimal in that sense, typically framed as heuristics or biases. There's a really beautiful, in 2016, cognitive bias codex, which I'll just show you as an illustration. It looks like this. And there's a ton of biases that have been mentioned and identified in the literature. But my worry is, whenever I see this, I always think of this, like the Ptolemaic solar system with all the sort of little epicycles of additional explanatory possibilities. So you always have the worry that, like, when you have, I think I've started doing a review of the heuristics and biases. I think I've come up to 115 known and attested heuristics and biases in the behavioral sciences literature. That for me tells me that I've got a model of 115 free parameters, which is chock-a-block full of free parameters. Basically saying I can sort of retrofit most behaviors onto like something that has been identified descriptively and shown empirically. So how do we go beyond, especially using ABMs as well, to maybe assist the fields of cognitive science and behavioral sciences to try and sort of sift out through the forest of observations of these heuristics and biases, and try and go beyond just what the human is not, as in not perfectly rational or not complete information, but to what it maybe tries to do, or what it is, and what is attempting to do within this model. And those are some of the things that I would, yeah, open the floor to the rest of the people. Sorry for the props.
If I may make a comment on rationality, it's very often mentioned with Tversky and Kahneman, and that they demonstrate an irrationality in human behavior. But I've also read a paper that if you move from the concept of money, which is usually the trade-off in Tversky and Kahneman's optimization stuff, and you go towards survival chances and having food.
Wanda, we cannot hear you so well. Can you speak up or closer to the mic?
Again, I thought my mic was doing all right.
This is better.
Better now.
Good. I repeat. Tversky and Kahneman are usually discussing irrationalities in human behavior in terms of monetary outcomes. And then sometimes we see some strange called irrational behaviors. But if you transform these biases into chances of survival and obtaining food, then suddenly it becomes, from an evolutionary stance, very rational behavior. And in that sense, I think a lot of these biases that we tend to believe that they deviate from an economic optimizing principle are actually old mechanisms that have grown in a socio-ecological situation and provided us with evolutionary benefits. So what is rationality here?
Yeah, no, I completely agree, because like stuff like loss aversion, for instance, makes less monetary sense if you compare $10 and like plus minus, but it may make a lot more sense if you consider like going to a river and being attacked by a crocodile versus going to another river that's slightly less good, but like, you know, that's not that much of a problem. So yeah, like I completely agree. And that's exactly why I think we need goal-oriented agent-based models, where like they're trying to do something within the ABM, not just necessarily optimizing for money or something. So going beyond the economics or bounds. And this is also why I try to bring the example of the Indonesian fishing communities.
Yeah, yeah.
As
what we typically try to do very often is to implement needs into the agents.
Yeah.
And the interesting thing is that you can have conflicting needs. So there's not a single optimum. Agents can also differ concerning the importance of needs.
Yes.
And it's even the possibility, if you have internal conflicts, to reduce the importance of a particular need as a kind of cognitive dissonance reducing function.
I'm happy you mentioned this, Wanda, because like genuinely that was part of what we came back with from Indonesia, was heterogeneity of weights put on these different choice considerations. Right now in the model that we have, we are exogenously implementing them, but we are exactly thinking about how to endogenously change parameters so that, for instance, if you're going bankrupt, you may start to devalue the importance of being a good guy on the port and upvalue the monetary aspects. But that raises a whole second set of questions of like, are you baking in the answer that you want to find within the endogeneity, which becomes really tricky. So like for me, this is why I labeled the title of my talk, The Importance of Being Human in ABMs. Because I really think there's a deep need, I think, to understand how the adaptation of agents will manifest, and thus also maybe try and gauge what kind of policies or interventions could be implemented to manage a complex human environment system. I think we really need to go beyond, especially like just the narrow field of economic consideration, and as Harco as well says, like norms, values, institutions. But that opens the, like, I think, excitingly, I think it opens the ABMs to stuff on cultural theory and stuff on psychology and like a whole host of really interesting fields that I think will need to be sort of incorporated within ABMs in some way. But then that becomes a question of what can they teach us and what can we teach them, the other way around. I think we've got 1 more minute, Davide. Sorry.
Yes, we have 1 minute. I've seen something's going on in the chat, so maybe somebody wants to say something out of that.
Yeah, Davide, thank you. Well, just to comment on one of your 3 points that you just left for a discussion, and I like to pick up especially the second one, which is about, and my impressions about this kind of possibility of you know, exploring especially ecological or evolutionary kind of, you know, approaches to understanding agent behavior and general rationality. And in an agent business model that probably we are very specifically focused on agents and behavior. So we invest a lot in, you know, maybe trying to provide a rich, you know, representation of behavioral models, and whereas probably the representation of the environment today in our agent business model is very trivial. And then it's just, you know, at best, you know, in some evolutionary game theory, ABM inspired is, you know, some functions that they pay off, and also representation of space, which typically is probably static or not rich enough to capture the co-evolution of agent behavior and environment, which is needed to speak about probably ecological rationality. And maybe we might probably consider, and this is probably, I don't know if this is what Bruce has in mind when he insists on the importance of context, but this is an example of probably context that we probably have to try to develop better representation of rich environment with a different kind of cognitive, artifacts as in your kind of idea. And now we're very, very behind this kind of possibility, and probably this could be a very good kind of step forward.
Thank you very much. That's an excellent point, I think. Also because if we are serious about making more realistic cognitive assumptions for our agents, of course we must also address the problem with the environment. And I think, as somebody who usually models organizations, I think that this is exactly spot on, because I think I cannot be satisfied by the way an organization is represented in an ABM. I'm not just referring on the static desks and chairs, etc., but also on all sets of environmental components of our daily work and life. So,
so yeah, the flow is always typical that if we have not possibility, we insist on maybe enriching the representation of agents at the expense of the environment.
Yeah.
And whereas probably could even be a good idea to maybe have even stupid agents, or try to relax or be simple in terms of agent behavior, but being rich in terms of environment. So this is in the trade-off. It's not by definition that that trade-off goes in the direction of enriching agent behavior.
Yeah.
That would often be the case in environmental modeling, where the environment is very richly represented and the agents are often little dots that just sort of flitter about.
Yeah, we are eating up the break,
sorry.
So I think we must stop. So there are 3 minutes remaining, so let's reconvene at 35. All right, so let's drink a glass of water, some coffee, tea, whatever you please. All right.
And if you have any questions, please feel free to email me of anything, obviously. And thank you so much for.
Thank you very much.
And everything.
Hello again. I think we're back. So the next is on hybrid forms of modeling. And I think the first two speakers will talk about microsimulation. And I have here in our program that Michele Bernasconi should be next. So, Michele, if you're there, the floor is yours.
Okay, thank you, Davide. Thank you very much. Very nice to see you again. And thank you very much for hosting me in this very nice conference and week on social simulation. The topic that I'm covering, I hope that you can see my slide. I have started to share the slide. Okay, thank you. Is slightly different. I'm not talking about agent-based simulation model, as Davide was going to say. I'm talking about microsimulations. We do simulation, but these are not exactly what is meant by agent-based modeling. Okay, we do a slightly different type of simulation, but I hope that there are connections, and certainly has been instructive for me listen the previous lecture. And I'm talking in this analysis of microsimulation with say something about tax evasion, which at some dimension, including about this behavioral aspect, behavioral models of economic agents. You use the term bounded rationality. I stopped using bounded rationality for this Tversky and Kahneman type of approach some years ago. So it's interesting that even if I'm say a mainstream economist, I have stopped using bounded rationality while you still keep using it. Okay, but then I I go back perhaps to this in a moment. Okay, since probably you don't know very much what is a microsimulation model, and in particular tax benefit microsimulation model, I spend a few words on that, and then I go straight to the point. Okay, first of all, it is a tax benefit microsimulation model, means that we are interested to models public policy, basically tax and benefit policy in this type of analysis. We use as feeding the model micro data on micro data set on individual, typically sample of economic agent. They can be individual, household, firm, that we have information on individual level, their incomes, their family structure, what they do as labor and this kind of things. And what then we do with this simulation model, we impose on them and study the tax and benefit that, given the institutional environment, they have to pay. And we do this in order to, on the one side, to account for the heterogeneity of the population, but our final purpose is to have some aggregate results to value social policy. So this is typically most of the time an ex-ante type of exercise. Often we simulate policy, perhaps proposed by political party or in the public opinion or by social observer and opinion maker to see what they are the effect. Okay, so basically, to just sum up, there are three basic components in microsimulation model: the micro data set with the characteristic economic and socio-demographic characteristic of the samples. There are the rules of the policy to be simulated, and then there are possibly the models for agent behavior. When we introduce a policy reform, in some respect, we want to model and suppose and make hypotheses how agents react to the policy introduced. This is the setup, even if, especially on the third point, how to model agent behavior, we in microsimulation analysis are in some respect very much behind standard, and is where the main difference are with the agents-based modeling. The typical in microsimulation model, there are, as in many simulation approach, such a simulation approach, two typical problem that we refer as external validity problem and internal validity. We want to assess the external validity of the analysis and the internal validity. And some question that I start to anticipate about the external validity is how to assess external validity in microsimulation analysis. And often, but this is a question, is whether external validity is sufficiently assessed with a comparison with actual external data. This is one question. And when you study tax evasion, you will see that this is a typical issue, because tax evasion is one of obvious dimension in taxation that you simply do not know, because this is something that typically agents do not want let the government or the society to know when and how much do they evade. So this is an issue about external validity. And then, of course, there are issues about internal validity that often require to check and eliminate programming bugs and coding error. But the question that we also address is whether we want to be some more confident when we talk about internal validity, about the level of confidence that we want to maintain about the conclusion and the causal mechanism in our microsimulation model. And this you will see, it immediately calls for issue of behavioral economics and behavioral modeling. So I tell you a little bit about the type of microsimulation model we are using in our analysis and how we deal with the problem of tax evasion, which is a specific feature of our approach. These are the co-author that I contributed in this over the year, and then our microsimulation model is called beta model. So the next slide illustrates a bit and give a bit more of an explanation of how a microsimulation model works and how the various steps and the problem of tax evasion is considered. So we have a database. These are information itself is information about microdata, consumption, income of the agents for the Italian population is a sample. Then this typical data comes with income that is disposable income. So with the disposable income, one can, when people is asked in survey about their disposable income, they misreporting the income that they have. And this misreporting is one of the first source of perhaps evasion. Perhaps individual and agents, when are asked about their income in a social survey, they are afraid of the type of information that they pass, even if they know that it's a social service or opinion service or demographic service, they may still be afraid about passing the information to the government through and the tax authority to this information, so they could underreport. So what we do as a first step in this model, we scale up, we estimate the level of misreporting and scale up the original data with on income that enter then the proper microsimulation approach in which we compute the taxes, the various tax expenditure of the agents in the model. This involves, obviously, since it's a sample, some reweighting procedure. It involves some test of conversion between simulated data and data from public registers. The important thing is, of course, what the microsimulation model actually does is since the input in the data is typically based on disposable income, even if perhaps scale up, then you have to make what is called net to gross income conversation. This is typically implementing simulation of the tax system and computing and using the simulation to compute on every unit of the micro data set the level of gross income. Then when we do, at the end of approaches, the test of conversions is to check whether the disposable income, which come back after all the process, is how it does compare with the registered data. And through that, we obtain an extra dimension of evasion through a discrepancy method. We compare the discrepancy, the distribution, the income distribution coming out from the microsimulation model with the actual register. And any discrepancy is interpreted and adjusted for a further level of evasion. So in sense, there are two levels of evasion, or two possible levels of misreporting. One at the level of misreporting to the social service or the democratic service, and one compare at this level, we check also for comparison with official registered data. This is what we do in this analysis. And at the end of the day, we obtain, I hope that the slide will come up, since there are a lot of data should come up, what is on the one side here, the true gross income measured in thousand on billion of euros, and €1,000, sorry, and here is disposable income. This is a tax schedule. The red line is without evasion. The black dots are the unit for which we have added tax evasion. And of course, when you have this data, you can do a lot of type of exercise. You can measure the aggregate level of evasion. You can measure the tax gap generated by evasion. You can measure the effect of evasion on the post and the post distribution of income, and you can also try to assess the welfare that is lost because of evasion, and do whatever exercise you want to do. Okay, so this is the type of setup that we have. Of course, in doing that, you have the possibility to make some control about also the how your data match with the registered data and the type of analysis that I anticipated before. For example, this type of exercise that I'm reporting here measure in almost 100 billion of unreported income in Italy, and this corresponds to about 25,000 of tax gap. And you do the kind of exercise that you can you think may be useful to judge the level of evasion and so forth. Okay, so this is the type of analysis that you can do. But what then you can do is you can use, and this is where the behavioral models come into the story, you can use the initial estimates of evasion and the initial estimate of all the system to simulate the effect of tax reform. Okay, and of course the issue is that when you simulate tax reform, you want to discuss and to think and to make hypotheses about what happened as a behavioral response of the change in the level of taxation in the tax reform that you are considering. And typically here you can do various type of hypotheses, and you may also have various type of microsimulation model. For example, you can say that the evasion rate, the amount of evasion rate for every individual does not change even if the tax level, the tax system has changed. For example, you may think we move from a progressive tax system to a flat rate tax system. What does it happen when you change the tax rate? And the first hypothesis, very simple, is using what we call arithmetical model, just keep the same constant level of evasion. You can use what is in economics or mainstream economics, a fully rational model based on a theory of economics prime developed by Becker, which basically is the economics, standard economics type of calculations of expected cost and expected benefit of evasion using the expected utility model. You can say that people, for example, start to have some bias in the way in which they consider the probability, and you may have a model with a probability of overweighting. Probably some of you familiar with this literature know that this model with probability of overweighting only are models called expected utility with rank-dependent probability. Or you can incorporate even more complex type of preferences. We mentioned already in this afternoon Tversky and Kahneman type of preference, where a major point, of course, is that they have a framing, and in the framing, in particular important point is the reference point in the preferences. So obviously, what is the reference point in this microsimulation is an issue that you can simulate, that you can make a hypothesis about, that you can try to estimate, and so forth. So we do this type of exercise, and for example, you can use this type of simulation also to see how the model fits the data that you have estimated. For example, among this model, which best represent the distribution of the tax evasion rates that we have observed in our analysis. So here, for example, you have the evidence that the beta mode are the estimate, the original estimate of evasion, and then we simulate the tax evasion rate, where these bar are the classes of true gross income, and we see that if we use the standard expected utility model, you have even more evasion that you expect. That you use overweighting probability, you have more evasion, but not as much with expect utility. If you use reference-dependent preference, you get much closer to the data. Much closer to the data, but only on the top level, on the height, not top level of income, but say on income level, in the middle, low middle range, and top range, not at the bottom here. This is an interesting effect that, for example, you may discover and you do not expect. All these people that evade more than even the theoretical model predicts is because when you are at very low level, yes, with the task schedule, you can properly report your income and benefit for all tax expenditure, but this has some attention cost that perhaps at the very low level, you just find easier not reporting income, and this is what we observe, and no model can expect. Okay, so this is a type of exercise that you can do, and then you can also simulate flat tax reform. I do not spend time on this because the time is going at the end, and I just go straight to the conclusion. And the conclusion, then of course, after behind me, Francesco Figari will tell you, explain more about micro simulation model, but my reflection and some of the questions that are in a sense similar to the question that, even if slightly different, in a more different way, thinking about the agent-based modeling you address, are, however, have a similar flavor. First of all, of course, first of all, the point is that about the tension that also in microsimulation model we have between external and internal validity. Typically, we often require internal validity, and in order to achieve internal validity, we proceed through abstraction and simplification, but this may become a bit at expenses of decreasing validity. So one question which was similar in a sense to the last point Flaminio made is whether is it better to be, from some respect, in a search for abstraction and simplification for internal validity, whether it's better to be parsimonious in modeling the social environment and the institutional environment, obviously, when you talk about social policy, or perhaps you can sacrifice a bit in modeling behavior. Obviously, fully rational expected utility model is much easier to model and to include in the analysis than the reference-dependent model and the first-in-Kahneman approach on framing. Obviously, that is much easier. So where should we save? In modeling the environment or in modeling the behavior? And this is one issue. Another issue, which also is similar to something that perhaps you anticipated, is how to evaluate ex post the prediction that microsimulation do from an ex-ante perspective. Okay, so this, I hope that I stay more or less in the time that you gave me. Thank you very much.
Good. Thank you very much, Michele. I think that now it's Francesco's time, because the Q&A is at the end. So
we've been told this.
Good.
Okay, so thanks a lot, and thanks Davide, thanks for the organization. I think you should now see my slide on the screen. Okay, that's great. So, well, in a sense, my task it is a bit easier, given that Michele already introduced the microsimulation, static and behavioral tax benefit microsimulation. At the same time, I hope to be able to add something to build on what Michele already presented. And I will focus in my talk on the potential links between tax benefit microsimulation, in particular behavioral microsimulation, and ABM. I come from the microsimulation part of the story, so please bear in mind this, in a sense that all what I'm saying is really open to discussion and to your suggestion. So if we look at Okay, so if we look at ABM and microsimulation, at least we agree as a starting point that we are interested in some sort of ex-ante simulation and ex-ante evaluation. And then the key difference is whether social interaction and interaction among economic agents is an important consideration. And this basically, it is at this point is one of the main difference between ABM that are really focused on modeling and simulating these interactions, and microsimulation, which basically do not consider this interaction. And so I tried to put together, based on a review in a forthcoming book by Kim and Edmonds, let's say the characteristics, basic characteristics of ABM and microsimulation model. Because one point, at least what one need that I really feel, is that there is a really need of methodological and terminological clarifications. And this is true even within the microsimulation literature. We talk about microsimulation, but then we know that microsimulation is really a wide strand of literature. And then in particular, when we try to have these two literatures, ABM and MSM, talking together, I think that really there is a need of clarification in terms of methodology and terminology. So this is my attempt, and then is then up to the discussion whether I got it right or not. So if we start with basically the basic characteristics, then I think we agree that in the ABM, each actor, each economic agent can be explicitly represented, so heterogeneity of agents is at the core of the model. And this, even if to some extent this is true for microsimulation as well, given that it's microsimulation, so the interest is at the individual unit level, unit which can be individuals, households, firms, but anyway, individual economic agent. If we look at if we consider adaptations, so processes of learning evolution and interactions between individuals over time, here is where ABM is really powerful, while in this sense, microsimulation cannot say basically anything. Representation of structure and space, ABM is able to incorporate very sophisticated representation of this, while the MSM does not. If we do not consider as space, structure and space, the policies, the policies that a government might introduce. So it's important also to have a clarification of what we mean by structure and representation of the structure. Interaction throughout the dynamic simulation, then following the individuals across time. This is something done in ABM, and it is something that somehow can be achieved in microsimulation model when we consider dynamic model. Interaction with either other agents and environment, again, interaction, so where ABM are really powerful and where MSM really lack, and then they cannot say much. Then microsimulation model can be exploited when we are interested in the evaluation of the impact of policies, in particular on representative samples of individuals, as Michele mentioned, at the base. At the starting point of microsimulation model, we do have data, microdata, which are representative of a given population. Then we can use the model in order to aggregate the results and to look at the distributional impacts. So having set up the differences and the contact points, we can say that the ABM are at the starting point are useful to characterize the social and economic interactions between individuals, while MSM are useful to have a policy evaluation and also an evaluation on individual well-being of given policies. When we talk about MSM, we usually distinguish between static, dynamic, and behavioral effects. And here is where also within the microsimulation community, more clarity is needed. So when we talk about static, we mostly refer to tax benefit models. They simulate income or other kind of taxes and social transfers. And these models are tailored to short-term analysis with a fixed population. Then the population can evolve in the medium and long-term perspective. And here we enter the area of dynamic microsimulation. But still there is the issue about induced reactions. So if we have a policy reform, which are the reactions in terms of tax evasion, as Michele was talking about, or in terms of labor supply, in terms of savings, in terms of housing. So how the behavior of individuals changes due to a new or a reformed policy. And here I think is where the contact points between the two methodologies are really important to be understood and to be exploited. Few examples, at least what I know, if we talk about ABM and dynamic microsimulation, these can be considered as complementary techniques that could be usefully integrated into a sort of hybrid modeling approach. One example is the Moses model for the UK. So basically in this model, the developer, the author, start from micro-level population data, so with socioeconomic information and characteristics in terms of age, race, socioeconomic status, marital status, and so on, and then use a dynamic microsimulation model and an age-based model to simulate individual states over the life course. Of course, the difference is that in the microsimulation model, these simulation and projections are made through a stochastic process, while in the ABM part, this is made through a rule-based process. And so the combination of the two gives population projections in terms of policy scenarios or demographic changes and so on. And so here my question, coming from the microsimulation part of the story, my question is really how then the rules are defined within the ABM and then modeled. And once we know that, this is important to understand whether the two kind of models can talk, in particular when we move to a behavioral microsimulation model. And I will back to this point in my conclusion. Then another example, and here we talk about a model, a dynamic microsimulation model, LaborSim for Italy, which is a dynamic aging, discrete event, probabilistic, and agent-based microsimulation model of labor supply. But here my question, and of course this question would be for the authors of this model, but Matteo Richiardi, one of them, cannot attend the workshop today. But the major point here is in terms of methodology. So what about interactions? So to my reading, the main focus of this model are on demography, migration, retirement rules, and education and participation choice through the dynamic microsimulation model. But my basic question, what about interaction? So I don't see where the interactions between individuals are modeled. And so my question again, where is the agent-based characterization of this? But having said this, there are plenty of policies which can have an impact on individual behavior throughout social and economic interactions. And how can we model the effect of these policies? And here I have just a few examples. One, of course, is the tax evasion example, and on this Michele has already talked about. Then there are other examples. So for instance, benefit non-take-up. We know that the benefit non-take-up is a process where, for instance, the stigmatization of individual is something that is well recognized as one of the determinants of the benefit non-take-up. And we can think that the stigmatization within a community, a local community, it is something that it is really affected by interaction. So to put it really simple, I think that if I live in a small village where all people are claiming a given benefit, I'm not stigmatized if I do claim that benefit as well. So there is an issue about interaction between individuals. So this just to give you a flavor of what I mean by interaction and what I think it would be really important to consider. But all behavioral microsimulation model that estimate the benefit non-take-up behavior, and in the UK, for instance, the literature is quite huge, do not take this into account. Or for instance, childcare usage. We know that Italy is characterized by a quite low level of childcare usage. There is an issue about cost, an issue about availability, but there is also an issue about cultural norms. So in some part of the countries, today, 2020, some families are not really willing to send their little kids to the nursery, kindergarten, and so on. It is an issue of cultural norms, and so issue at the end of interaction between individual behaviors. Or another example, tobacco and alcohol control policies. Again, here we see that there is a huge issue of social interactions. There is an issue of regulation, and also an issue of fiscal policies. And so the different modeling setup could be really, really useful to have a clearer idea of what happened. So basically, behavioral tax benefit microsimulation model allow to model the individual reactions to new policies induced basically by monetary incentives. If we focus on labor supply, for instance, where the behavioral microsimulation model are most used, the effect comes through substitution and income effect. But still, they ignore the interaction between individuals, they ignore social adaptation. And this, I think, it is something quite important to consider, and it is something where ABM and the behavioral microsimulation model could do something. I put in my slide a bit on the behavioral microsimulation modeling framework, but I don't have, I think, time to go through it. So I think that I will just say a few words about this, because in a sense, when we talk about behavioral microsimulation model, very often we talk about labor supply. There are other examples. Michele showed something on tax evasion. There are examples on consumption choice, housing choice, but most of the models deal with labor supply. And this comes in the form of static structural discrete choice model. Structural because they provide a direct estimation of preferences over income and hours of work. So there is a utility function with a given functional form, and the arguments of this utility function, as stated in the basic and standard economic theory, are income and leisure. So these are the two arguments, and this model allows to provide a direct estimates of these preferences. And are discrete choice model because the possible alternatives, let's say in terms of labor supply, for example, are not on a continuous set, but the choices are limited to a discrete choice set. So we do estimate this model. We do come up with an estimate of the preferences over income and hours of work, and we can then use these models. I just go here from the schematic representation. So on the left, you can see what we have in the pre-reform scenario, where we estimate and simulate a budget set derived using a static tax benefit microsimulation model based on survey data. We estimate the labor supply model, and so we estimate the preference in terms of income and leisure. We keep these preferences as fixed, and then we change the policy. We introduce a hypothetical or real policy reform. We derive a new budget set using a static tax benefit model, which allows us to simulate, to impose in an arithmetical way the new income tax or benefits or whatever. And then using this new budget set, we can estimate the labor supply. So we can see which are the behavioral reactions, for instance, in terms of labor supply of the individual. But still, these behavioral reactions are individual behavioral reactions. We can aggregate at the end these individual behavioral reactions, but these are processes, estimated processes that do not take into account interaction among individuals. And this is really I think the most important limitation of the microsimulation model. Microsimulation model, a labor supply microsimulation model that can be extended, so to somehow consider the impact of the environment. Well, at the beginning, I mentioned that when we can say that somehow the microsimulation model takes into account the representation of structure and space. I refer to this point. For instance, childcare. In a recent application, we estimate a discrete choice model, a joint of labor supply and childcare use. And in this model, for Italy, we take into account the constraints in terms of cost and availability of childcare. So we do take into account the environment, but we do not take into account the interaction among economic agents. And so, having said that, this is my last slide. How can microsimulation model and agent-based model interact? Agent-based model models individual interactions and behavior through built-in rules for individual agents. And so this is a question I posed at the beginning, but how rules are defined and modeled? I guess that the answer is really model dependent, but coming from a different literature, this is a sort of basic question that I would really think about. Then ABM are useful to introduce heterogeneous agents with distinctive behaviors that are not mathematically tractable. And so here the point is whether these are compatible with, for instance, a utility maximization process embedded in a behavioral microsimulation model. And the last point is the one that Michele already focused on, which is about internal and external validity, which is crucial for microsimulation model, and which is something that in some cases is not considered sort of ambition for ABM. And so I conclude saying again what I mentioned at the beginning. I really think that a methodological and terminological clarification is needed at least on the microsimulation literature, which is the one I know better. And so I really thank the organizer for this occasion, which is, at least for me, a first step in this direction. Thanks a lot.
Thank you very much. Thanks a lot, Francesco. Very informative presentation. And thought-provoking also. So now we move from microsimulation to system dynamics and ABM. So if Lisa, if you are with us, I think you are, yes? Yes. Could you please share your screen? But I think first Francesco should unshare his screen, I guess. Otherwise... Great. Thanks.
Okay. First of all, can everyone hear me?
Yes.
Yeah.
Okay, very good. All right. And you can see my presentation just fine?
Yes, yes.
Oh, wonderful. Okay. So I've titled this, well, Davide, thank you very much for this opportunity. This conference has been amazing, and so far as this workshop is concerned, it's very interesting that so many different perspectives being brought to bear on so many different facets of considering agent-based modeling and thinking about the boundaries of agent-based modeling. So my talk today focuses on building middle range theory at the boundaries of ABM. And so for the focus of this workshop is exploring the boundaries of ABM and thinking about what other perspectives can be brought to bear and offer to ABM. So my slant in this perspective, in this presentation, is going to be focusing more on the system dynamics side and what system dynamics in particular could be, what perspective that could aid or enhance agent-based modeling. And one of our other mandates for this workshop is to focus on questions over answers. So hopefully that those are things that I will accomplish here today. So to begin, what I mean by middle range theory, just to start with just a set of, to know, what my perspective is on this. And I'm just borrowing from the Mertonian perspective on what middle range theory is. And my focus is on explanation and in the generative social science tradition that has been described by Epstein. And so I am so thankful within the context of this conference that as Epstein described inverse generative social science is that it is not the end of theory, that there is still a role of theory in agent-based modeling and all sorts of applications. So the boundaries that I'm exploring today is to build middle range theory through the development of agent-based system dynamics hybrid models. And so I'll describe a little bit what I mean by that, but for simplicity, I call them ABSD models because otherwise I have a whole mouthful of stuff to say. So today, the two foci that I have are thinking about why and how. So those two perspectives. And so for the why perspective, to begin with, I want to give a little brief background to set up a couple of reasons why I think that there's utility and value in at least thinking about and considering hybridizing agent-based modeling with system dynamics models. And for one, just to hold in our minds this perspective that I'm drawing from, this model-centered epistemology that I have adapted here from McKelvey. And I'm just bringing here the point that when theorizing, a lot of folks think about and consider theorizing, they're thinking about, especially maybe perhaps most coming from an economics background, thinking about theorizing from an axiomatic base, the thing I have circled here, thinking that you're drawing from an axiomatic base and from that you're deriving theory. And what McKelvey says, and that's applicable to generative a social science perspective, is that really one perspective on developing theory is that you don't, this probably should be like more of a dashed line here, but really that when you're thinking about theory, that developing simulation models has utility in bringing multiple perspectives together in order to iterate and develop theory. So you're not just going, you're drawing from the phenomenon, but the models in effect interface between, provide an interface or a nexus, I guess is a better word, between theory and phenomena. And they bring together those two aspects, and you can go back and forth in order to develop theory, middle range theory from that perspective. The other thing that to hold in mind as we talk about the why of hybridizing is to consider what the values are, what the rough characteristics are between when you consider agent-based models versus system dynamics models. And so I'm going to hew more toward describing the system dynamic models in this sort of, rudimentary chart here. But that, system dynamics models are based in control theory and use nonlinear differential equations to describe accumulations and rates of change in what are called stocks, which you can think of, if you're not familiar with ST models, as just big bathtubs full of whatever is being measured. And flows are outlets, and between those two, between bathtubs. The other thing that characterizes as system dynamics models are feedback loops. And these stocks are homogeneous. There's a homogeneity when you consider stocks. That is, again, that's distinct from when you think about collections or groups of agents, where heterogeneity is really what is focused on. Homogeneity is the way that you need to go with when you're considering a system dynamics model. There are other distinctions too, but I hope that this chart just gives you a sense of how the two types of modeling methods compare to one another. So thinking again of from McKelvey's perspective, and thinking again of these distinctions between the model, how do we leverage those, and why is it a good idea to leverage these differences and maximize in the ways that they are complementary? And so the one reason is, I believe, is that one advantage that system dynamics has is that I really believe that it can aid in conceptualizing multi-level transitions. And this was brought out during the conference by Robin Pershaus, and I think he put a very similar diagram that's I've always known as Coleman's boat. And thinking about transitions, macro, micro transitions, and I guess I'm thinking, from an ABM perspective, most often thinking about micro, macro transitions. But there's also within discussions from different perspectives that there is the possibility of having macro transitions that were first kind of erroneously maybe described by Weber, thinking about transition states between going from one macro state to another macro state, going from
You're mute, Lisa. Your microphone turned off.
It's I'm sorry. Probably I caused this.
Oh.
You didn't like what I was saying.
Essentially, I'm sorry, Lisa. I don't know what.
Oh, no.
I love to call him on boat, by the way. I'm sorry.
Very good. All right. Well, thanks for confessing. So one of the things that one thing that system dynamics offers is it does offer a unique way to model and consider transitions, macro to macro transitions, that are probably more difficult to conceptualize within the constructs and within the universe of thinking about agent-based models. So that's one perspective. Again, I think that you could just say, well, like it's easy, maybe thinking on a broad institutional level, it might be easier to conceptualize and the assumptions are made more clear through using system dynamics models to model institutional norms, for example. So that is one perspective, but also on the micro level, system dynamics models can be embedded within agents to model the effects of institutions on agent action. So those are all considerations that you don't have to think necessarily how system dynamics can aid just on the macro level, but also as well on a micro level within individual agents. System dynamics can offer a perspective into conceptualizing complexity and whether you think that levels and transitions and maybe having a meso level here is maybe a red herring. Whatever your perspective is, I think that this diagram is still useful in describing the advantage that system dynamics can bring if institutions are a factor and norms are a factor that you want to consider within a modeling framework. The second reason is that system dynamics can aid in conceptualizing dialectics and theory building. And this really dovetails, I think, well into my thinking and into what Davide discussed with bounded rationality. That there is so let me back up a second. So along, you know, an organization theorist, Thompson, in Organizations and Actions, posited that and discussed how organizations are better able to survive if they're able to couple together in a loose way to rationality and indeterminacy. So that organizations need to maintain, to survive well, organizations need to maintain a means-ends chain that is solid and clear and direct. But organizations also have to respond to the environment and to their environment and to be able to adapt accordingly. And what Thompson coined as loose coupling has been taken off as a metaphor or an image in the literature. And I think most notably by Weick and others that have extended this idea of Thompson's of organizational survival to think about how it is possible to preserve integrity and distinctness, and it's at the same time it's also and also responsiveness, and to have these in different spaces within the context of an entity or a model or a person. These things are what are called loose coupling. And so there's a dialectic to there that's maintained by loose coupling, that those two elements are preserved. And you know, this is just my sort of diagram of that. So going back to McKelvey's perspective on having a model-centered epistemology, one thing I think that thinking about bringing in system dynamics is that one of the strengths of system dynamics is that it's a deterministic approach to modeling, and for that it could be, when it's brought to bear with the strengths of agent-based modeling and being able to be more adaptable and more agile and fox-like. Nathaniel Osgood calls system dynamics models hedgehogs and ABMs foxes, and I think that's a really good description. Because bringing these together, I think, as a hybrid model is a way that both of these perspectives and loose coupling can be represented within a model. And whether that's within the context of an agent or within an organization, that scale can be determined. But system dynamics offers a way into doing that. I think that other perspectives, it's not as easily facilitated. It's not, I don't think that it's that it couldn't be done. I think it's that rather that it helps with apprehending complexity and dealing with that aspect of our bounded rationality as we approach model building. So this is just a schematic representation of how, if you think about equifinality and how theory can be approached through different means, and how there are different ways that things can occur and different mechanisms that can explain something that are accurate. That one way into this, bringing these perspectives together is through developing hybrid models. So I think that those are two reasons that I find interesting to think about in terms of discovering how system dynamics can augment agent-based modeling. So the second perspective, question that I'm bringing in, considering, is to think about how this can be done. So the first part was sort of thinking about a couple of reasons and presenting a couple of reasons why. And I want to take a couple minutes here, I don't have very much time left, but to consider just how to begin one way into this and how to be able to bring these two perspectives into theory building. So I think about the classic modeling processes that undoubtedly you all are familiar with, and they're just very similar and iterative, and across whether you're doing an agent-based model, the process is very similar, and the way of thinking is very similar. I think that's an important point to bring out, because there is a way to think about you can mine those similarities in process and think about how to think about how to bring models together. So the first principle drawing on these process perspectives is that to understand first the distinctions between agent-based and system dynamics models. And this is a chart that I had up before previously, but just to consider that these distinctions are spaces where that the two modeling methods can really complement one another in bringing forward a perspective. The second principle that draws from the process perspectives is to harmonize the architecture with a theory-centered logic. And by a theory-centered logic, I'm not saying draw from necessarily an axiomatic base to begin theorizing using a hybrid architecture, but rather to begin with underdeveloped theory. And, and it would be, as Jens and Davide were speaking, I was thinking that, it is true that much cited and little used, that idea that has been brought out about bounded rationality is that that bounded rationality might present itself as something that can be harmonized and through this type of architecture. So simple theory is underdeveloped theory. It's theory that Davis, Eisenhardt, and Bingham have described as having few constructs. It hasn't necessarily, it's theory that is pervasive maybe within a discipline, but hasn't risen to the level of agenda like maybe bounded rationality has. The complaints about bounded rationality or the musings about bounded rationality is that there hasn't emerged a research agenda. So basic theory is a good starting place to begin to build this. And then to think about how these two methods can interface with one another. There's numerous ways that this can occur. I have several examples here, and I'm just gonna, for the sake of time, I'm just gonna list one of them. But one way is that an SD submodel can be nested within agents of a larger of an agent-based model to trigger agent state transitions, for example. So there are numerous ways where these two methods can interface. The third principle that I would like to draw out, derived from those two process perspectives, is that contributions should need to be clarified, and next steps and iterations, and modeling is iterative. And this is an example of a causal loop diagram that is classic in system dynamics methods. And it's actually one strength in engendering, and one thing that can be used to enhance where agent-based models can interface with system dynamics models. And so these types of system dynamics has a whole tool set of scripts and causal loop diagrams, reference modes, all sorts of things within that have been cataloged and studied. And those things help to aid where contributions need to be made within a model, and they also help clarify what the next experiments or iterations may be within a modeling process. So these three principles are really just condensations of these process perspectives and of Davis, Eisenhardt, and Bingham's work in building theory with simulation. So I just wanted to present that too, just to have a way in, not to make it a black box about how these are combined, but to begin a discussion about ways in which these two methods can interface. So thank you very much.
Thank you very much. Thanks a lot, Lisa. Lots of things to think about. And so we have up to 45 for questions or comments on the three presentation. So you can either open your mic or raise your hand or...
David, I have a question.
Sure, go ahead.
For Lisa. I just posted that on the chat.
Okay.
It's about the practicalities of the of this combination of ABM and SD models. First is the validation of the correct level of aggregation in the system dynamics model. How to do that, and the second thing is how you operationalize and these two types of modeling, because SD models are operating continuous time.
Yeah.
So and that's not the case of ABM. So yeah. For example, in terms of software combination, how to do that?
That's a very good question, and so that's a big question too. It's an excellent question. So I think in terms of validation, that's gonna, how that's approached and how murky that becomes becomes a question of how the model is interfaced. So my suggestion and what my approach has been to this is, to the extent that I can extricate parts of the model out and do sub-validations within the model building as they're being put together as in a whole. That helps. That helps as you're building and as it's being iterated. To just, it doesn't get an external ability, of course, but it's just, what it helps to do is just to see is, if, particularly with system dynamics models, there's reference modes that you can see if the pattern that is being produced is consistent with what you would expect given the configuration of the structure that's being designed. So so in that box, so how complicated and how murky it becomes depends how intertwined the two are. So when you have, like, if you have a system dynamics model embedded within an agent, that it becomes, you can validate within that system dynamics model, but then it becomes a lot more tricky to validate outside of that once you're interacting. Now, so all the normal problems that go with developing parameters, and so, but there is possible ways that you can have them more demarcated within a hybrid model. So some folks may have just one linkage, so it is more clear how to separately sort of validate those, and then when you bring them together, it becomes a lot, in my view, more simple to validate the models. In terms of the role of time, it's like you can operate within a discrete time period within system dynamics. It is possible. They are not, if ontologically and epistemologically, the two methods, they operate in different spaces, right? So so that, again, so you can have that separate validation within it. And you can, so because they're operating within different spaces, they don't necessarily incompatible together, but within the context of a interface. So one software package that I use is AnyLogic, which is that facilitates those things. So there's other packages and other ways that could be done. One advantage of that is that you could build within something like Vensim and then import that in pretty easily. So I hope that begins to answer that. That's a big question, though. That's a great question. I hope I addressed a little bit of that at least.
Yeah, sure. Yeah, thank you.
Nice. Other questions? If not, maybe I'll ask a question for Francesco and Michele, because I think Francesco, stressed the fact that interactions are not there in microsimulations, and this could be a problem. At the same time, the question is, well, is it? Meaning, I mean, shouldn't we be pragmatic with modeling? So if the model performs in a certain way, aren't we just exercising our selective ignorance, as the philosophers would tell us that we do with modeling? So we are basically selecting out what it is not relevant, and sometimes interaction may not be bringing in all that positive impact on our output. So, I mean, does this fit, for example, the simulation that Michele presented, the fact that interactions are not there and therefore maybe there are there's too much that we don't know? Or maybe, I don't know, does it make sense? Or what I'm asking, or it's just
if you want, I can reply for.
Yes. Okay.
We have chatted on the list, Michele and Francesco, about that.
As usual, you try make a step at the time. Okay, the expected utility model, the model of crime, Becker model of crime applied to tax evasion is a model of individual decision making. Okay, you just evaluate the benefits and the costs from a strictly pecuniary economic perspective. Okay, so we did a little step forward, okay, including this idea of a reference dependent, that you look at your past decision, basically. Your reference income in that case only depends on what you did in the past, what was your income in the past, and what are the expectation of changing in the income without interaction. But of course, yes, there are a lot of social interactions going on when people make a tax evasion decision. There are stigma, there are shame, how different stigma is for shame, there are moral rules, all this. And there is a large literature now, behavioral economics literature, including theoretical, this side, and doing experiment on this other type of social effect, behavioral effect. Yes, I think that would be very nice to bring in microsimulation analysis these effects. But up to the point, up to the moment, we have to say that not even tax evasion is normally addressed in microsimulation model. Okay, even in the standard, most simple way, usually is ignored. And one reason is ignored because in one criteria for validating external validity, at least in microsimulation model, is comparing your data with outside data, registered data, and typically registered data do not have evasion, so it's very difficult to measure evasion. So we don't have a measure to evasion. So it's very difficult to say which model and how whether it fits, and so it's very difficult. But I think step by step we will arrive, and I think agent-based modeling is a very good approach to bring in this type of analysis.
Okay, thank you very much. Our time is up, so I think we can have a short break, and we reconvene at 4:50. Okay. All right. So I think we're back for the last part of this afternoon. Well, we are perhaps into the evening, I guess. The next session is about machine learning and statistics in connection to ABM. And I think the first in line I have here is Matthias Müller. So Matthias, if you are there, please share your screen, and your floor is yours.
Thank you very much, David. And I hope you can see my screen. So
now we can, yes.
Okay, good. Can skip this one. Okay. So welcome everybody. My name is Matthias Müller and I present today a joint work with Kristina Bogner, Johannes Dahlke, Thomas Berger, Andreas Püker and Bernd Ebersberger. I think Johannes is already listening. Kristina unfortunately still is in another meeting. She will maybe join later. And Raffaello asked me to use this presentation also to introduce to you a little bit what machine learning is. The problem is I'm not an expert in machine learning. Quite the opposite. I will try my very best to stay on a really shallow level so that everybody understands what we are doing. But for details, please consult somebody else. So the title of our work I present later is More Than Meets the Eyes, Machine Learning and Agent-Based Modeling. And usually I start any presentation on ABM with a slide like this. And the big advantage of being participant of the SSC.
Matthias, sorry to interrupt you, but it seems that we can't see the whole screen. So there's a part of the slide is there's a black kind of thing whenever you click probably on. Can you just try to reshare your screen and yeah. I'm sorry, excuse me, but
no worries. So I tell Zoom to share my screen.
Pick up the window.
Do you see now something?
Yeah, better than before. Yeah. Okay. Yeah.
So for my screen, everything looks like normal. So
so now it's readable. Yeah, there's these kind of black straight are just peripherally. So don't worry. Go on.
Okay. So thank you for letting me know. Where was I? Usually when I have a presentation on ABM, I start with a slide like this explaining what ABM is. And luckily we're at the SSC and hence I can gladly skip this part. I just assume that everybody knows the basics of ABM. And although I'm pretty sure that most of us share a common perspective on ABM, I think there are still some open challenges in agent-based modeling. And you can extend this list as much as you want. For example, Michele has a nice article also discussing some of these issues. For example, computational efficiency is still a big problem. When I started using ABM, I had a small laptop. Now I'm working on a high-performance computer with more than 50 nodes, and still I'm not satisfied with the computational efficiency of ABM. We are lacking some kind of common protocol to communicate and describe our models. So far, the agent behavior is quite simplistic. If you want to convince somebody else to learn agent-based modeling or to get to know in agent-based modeling, there's still a high investment this person has to do to actually learn ABM, to do some programming. We have some open methodological issues. There's still the debate on keep it simple versus keep it descriptive and all this stuff. And our idea was at the beginning to see what is possible through machine learning to deal with these issues. And the question now is why machine learning? And machine learning is a quite popular approach currently. You maybe have seen something in the news that machine learning currently is better at chess than human players. Quite recently, they showed that they also perform better in Go, which is a more complicated game. Machine learning is better in skin cancer detection than human beings, but also some side areas, for example, ego shooting games, where they showed that machine learning algorithms perform better than human counterparts, not through better reactions, but through better team play. In our common daily life, we see Siri, Alexa, Google Now. We have video surveillance, email spam filters using machine learning, but also autonomous driving, which use this kind of approach. So what is machine learning? There's a common definition you see in the literature, and that states that it's a field of study that gives computers the ability to learn without being explicitly programmed. And at the bottom, you see a really simplified version of any machine learning algorithms, which basically has the idea you give it some input and you define what the output should be. And the machine learning algorithm tries to find an internal model. It's learning the internal model to perform as you want, to perform the transformation from the input to the output. And if you continue on reading, there are some appealing features usually mentioned when you read something about machine learning. It's unbiased, as nobody is telling it how exactly this model should look like. It's capable of processing huge amounts of data. It's flexible for many uses. Meanwhile, I would say it's user-friendly and easy to use. For example, in Python, there are many software packages. There's also TensorFlow from Google, which you basically can access via a web browser. And as I said, and this should not be underestimated, it's a little bit hyped currently, machine learning. So usually machine learning algorithms can be subdivided into two broad fields. The first one is called supervised algorithms. And the difference between supervised and unsupervised simply is whether you give the information what the potential output should be. So whether the data you feed into the machine learning algorithm has some labels. If you're in the realm of supervised machine learning, you usually see the differentiation between classification and regression. And for unsupervised machine learning, there's clustering or, for example, anomaly detection. However, there are also in-between levels. For example, semi-supervised machine learning, deep neural nets are sometimes not really attached to supervised or unsupervised machine learning. So this is just really broad and not so detailed overview. Let me continue. There are many different algorithms which are used in the literature. Most of you are probably familiar with neural networks, as it is the most prominent one. But if you dive deeper into the literature, you see something like k-means, Gaussian mixture, hidden Markov model, linear regression, decision trees, random forest, nearest neighbor, naive Bayes, and so forth, of course. And these algorithms can be used for quite different tasks. Regression, classification, I already mentioned, but also for association rules, for dimensionality reduction, for optimization or reinforcement learning. So this is what I mean when I say machine learning is quite flexible. There's basically for every task at least one algorithm, or at least one task can be used by one algorithm or even more. So to show you what machine learning can actually do, I tried to find a nice application this morning, and I came across a website which is offering to make a nice video if you just enter some text. So instead of going more into detail what we did via slides, I thought I show you what machine learning can do by basically using this website, which made a nice video out of our abstract. And I hope you can hear something.
I think for me, the audio isn't quite coming through. The audio.
Yeah,
you honestly say the audio is not working?
No.
Okay, that's a pity. Okay, let me just describe what I did. There's a website where you basically just enter the text, and based on your text, it is making a nice video. You couldn't hear it, but it's even having some kind of elevator music. It automatically finds some pictures to underline the story you want to tell. And this is also based on machine learning. So the question now is, what can we do for ABM with machine learning? And me and my co-authors try to find what has been done in the literature through a systematic literature review. We use Scopus. I think the search was done at the end of 2019. We identified some keywords The first set of keywords describe machine learning. The second set of keywords describe agent-based modeling or multi-agent systems. And as a result, we found 397 articles. And from this set of 397 articles, we excluded 209 papers due to irrelevancy. And yeah, let me continue. How did we classify the papers we found? We used a three-dimensional mask. The first dimension concerns the objective the authors had when they used machine learning for ABM, and the first objective we found was making the model more accurate. So this concerns, for example, the quality and number of data and assumptions. The second objective authors had in mind when they used machine learning was the computational efficiency, which directly relates to the challenge I introduced at the beginning. The third objective concerns the verification and validation, which is also still, in my opinion, a big problem, let's say, in the field of ABM. And finally, some authors used machine learning to enhance our understanding of the model. As a second dimension, we looked into the publications and checked where the machine learning algorithm has been applied. So we consider that there's basically three steps when you use ABM. The first one concerns the conceptualization and parameterization. So where you define the problem at hand, you define some key characteristics, who are the agents, what are they doing. The second step is then the translation of this conceptual model into a computational model through a dedicated environment, for example, NetLogo. And finally, as the last step, we consider the model analysis as everything which uses the output of a simulation. This includes looking, for example, for emergent phenomena, for some patterns to arise, but also the validation and sensitivity analysis. As the third dimension, we use the machine learning task I introduced at the beginning. And this is then the final evaluation mask, where we try to sort in and rank every publication we found in the literature. So this is a total overview. In contrast to our initial expectations, we saw that machine learning has been used for ABM and in ABM not quite recently only, but also already at the end of the 1990s. And it's gradually increasing, but I would say just based on this result, it's not a new idea to combine machine learning and ABM. This is also an overview indicating the publications, whether they are used mostly in the conceptualization step, the implementation step, or the model analysis. And here we see that by far the majority of approaches focus on the ABM step implementation. And if we now continue and see the objective, the second level here, we see that the majority of papers try to do so in order to increase the accuracy of the model. And finally, the most common machine learning task we found was the reinforcement learning approach. And now we dive a little bit more into detail. This is the whole set of publications that addressed the accuracy problem in ABM. This is Avulia in an Avulia diagram. You see that the overall task to improve the accuracy has been approached by all three ABM steps, but the majority, as I said, try to do so by the construction and implementation of the ABM. Amongst these, reinforcement learning was the most common machine learning task, which covers in total 135 cases, which, considering the 188 publications we found, is indeed the majority. But also other avenues have been found. And the question now is how detailed I should recap on this, because I know that the next three speakers also have quite interesting talks on this. But so let me just briefly go over the results we have in our paper. So the main step tackled in order to increase the accuracy is the construction and implementation of a computational model. The common claim here is that in order to make a more accurate model, we have to tackle the problem of two simple agents, which usually behave through what happens if conditions. And for this, Q-learning was a quite prominent approach. However, some papers also try to enhance the capabilities of agents simply by equipping them with some regression or classification capabilities. However, interestingly, we see also that the problem of accuracy has not only been tackled by making the agents more intelligent or more human-like, but also, for example, by using machine learning at the first step of the first ABM step, for example, by analyzing newspapers, and the information and patterns found in the newspapers has then been fed into an ABM. The next case, the next set of papers try to increase the understanding problem, which is with 27 publications still a lot in my opinion. And here we see, for example, that not really surprisingly, most publications do try to increase model understanding through the model analysis. And this, for example, covers the classification of data, the regression of data, or dimensionality reduction, and so on, so on. The next step, which considers only 6 publications, is the objective of validity. And interestingly, this has been approached through all ABM steps. One really interesting example is the work of Lamberti, which will present, I think, directly after my presentation. And the problem here is, how can we increase the validity of an ABM? Most of them try to tackle this problem by making an intelligent data parameter sweep to walk through the potential results of an ABM and then compare the result to the empirics they found. And this search for the best parameter setting is then performed through some kind of machine learning. Finally, only 4 papers try to increase the computational efficiency. And I think the only one really worth noticing, in my opinion here, because it's something different, is, for example, Silva, who try to analyze how many similar agents they have to represent in the model, or how many agents they have to represent in the model, and hence reduce the absolute number of agents in the model, and hence also decrease the computational load of their model. So this is just a quick overview of what has been done in our paper. We go a little bit more into detail of the potential cases. Let me just quit with some few conclusions. So as I said, our initial expectations were that machine learning is quite new in the field of ABM, which cannot be, which is not true. There are many, many different approaches, many different authors trying to use machine learning for different purposes, despite the fact that reinforcement learning is the most common use case. However, especially when it comes to these side papers, or let's say the papers who try to use machine learning on something different than on making the agents more intelligent, quite often we see that it's a proof of concept level only. So often we saw that the authors proved that this potential, that the application is there and that it is possible. However, most of the time we see that we miss still the proof that it's better than, for example, using statistics or other methods. And with that, I would say thank you.
Thank you very much, Matthias. So we now move to the next, which is Francesco Lamperti. So if you could please share your screen, and the floor is yours.
Thank you. Okay. Yeah. Can you see my screen?
Yes.
Good. Okay, so many thanks for giving me the opportunity to present part of my research here, and many thanks to Matthias for the wonderful introduction, which really summarizes quite well to me the kind of application that have been done so far in the literature, trying to discover how machine learning can be useful for ABMs. Today, I'm focusing on a kind of application where we basically build, we use machine learning techniques to build a meta model, to build a surrogate for the model in order to save computational time and then to have more flexibility to explore the properties of the model. So this is briefly the outline of the talk. So I will start with some introductory background very briefly. And then I will provide you some information about the main results that we had in a paper about the use of these surrogates for calibrating ABMs. And in a more recent application, we are moving to sensitivity analysis. So usually what policymakers, they ask us as economists or social scientists more in general are realistic insights on policy implications. And in case we have models that would like to deliver this policy implication, we should be able to provide a calibration of these
Francesco,
models.
sorry to interrupt. We can only see your first slide. I think we can only see the editor or the presenter mode, and we can't see your slides.
Okay.
Maybe
sorry for this.
use the other screen, maybe. Or, yeah.
I'll try. Sorry.
Sorry for the interruption.
No. Don't know exactly how I.
Maybe try to unshare and share again on a different. Oh,
I'll
something
try.
is coming up. Okay.
I'll try.
Oh, but it's all blank.
Can you now see the
No,
screen?
it's just blank.
Now?
We're back at the editor mode. Maybe it's worth just going through this and just, if you just press there, perfect.
Yeah, okay. Sorry for this, don't know exactly why. Okay, so, what I was saying is, if we have a model that we think can deliver policy implication, usually policymakers, what they ask us are recommendations, and usually they are interested into quantification of the effects of policies. In order to provide this, what we usually have to do is to calibrate the model relying on the empirical data. So what we have done is to apply the framework that I'm going to describe to two models. And in both models, what we take as an input are time series, as this is the standard approach that is used in macroeconomic ABM and financial ABM, where in most cases, the only information that you have about the real system is at the aggregate level, or at least this is the information which is most usable in a direct way. So what we usually do is to start with the empirical data set. We analyze the empirical data set in a way to identify statistical properties that characterize this data set, and we can call them stylized facts or moments. And then what we do is to use the initial condition and the parameters of our model to tune it in a way that once we find a satisfying configuration, it can produce a synthetic output whose statistical properties are close to the one of the empirical data set, at least in some regime of the model. And then it's a matter of the modeler to explore the model and understand under which conditions and why these behaviors they can emerge. So in a few words, our approach to calibration entails first a parameter space where we sample points, and then we ask the ABM to evaluate these points. Then we have a calibration test, which basically means that we have to understand whether the synthetic output of the model is in a way similar or resemble the empirical properties that we have in the data. If the test is passed, then we retain this point in the parameter space as the best calibration point. Otherwise, we move to another candidate and resample the parameter space, evaluating a different parameter. In doing that, we have some challenge. So for example, this is a table that I took from a JDC paper by Jacob Grazzini and co-authors, where they try to estimate a quite simple financial ABM with different approaches. And in their machine, it takes really days, months in order to perform all these estimation steps with a degree of parallelization equal to 1. Then, of course, one can, as Matthias was saying, increase the computational power it has access to. It is very expensive, but nowadays it's around, but still it's the most difficult part of the job is simulating the model. So sampling the parameter space is relatively cheap. The big problem from a computational perspective is evaluating the ABM. Running the test might be cheap or not, then it depends on the test. For example, if you just have to compute a mean over the simulation, it's very cheap. If you have to estimate a distribution and you are especially interested in detail behavior, then it might be a bit more cumbersome, but still it's relatively cheap. While the final decision whether to retain the point or not is cheap. What we did with this approach is to basically exploit some machine learning technique in order to construct a meta model that basically goes from the ABM evaluation to the final decision of whether this point is a good approximation, provides a good approximation of the empirical properties of the data or not. Another challenge that we have is that the parameter space of ABMs is always complex, is sometimes complex, is sometimes rough, it's sometimes characterized by nonlinear behaviors. This is, for example, a chart that I took from a previous paper of mine, where I basically used a measure of the distance between the dynamics of the model and one of the data, and I tried to explore two relevant parameters of the model to see how different combination of parameters, they provide dynamics that fit with the one that we observe on financial markets. And here is what I found. So we have abrupt changes if we just move from, if you slightly move in the parameter space. However, we need to discover this structure. Discover this structure is very important. So we have to, it's important for the model and also for the policymaker to know how the model behaves and which should be. To do so, we need to build up an emulator which is able to take into account these possible nonlinearities and these abrupt changes. And what we propose is the use of graded boosted trees. So basically the idea is to use a classification setting where we are interested in discovering whether we have a good calibration, so calibration that fits the data according to a criterion that we can determine, that the modeler can specify or not. And then we use the different decision trees and we let the algorithm learning over the relevant trees to keep and the trees that the algorithm can remove. And it can also optimize the loss functions such that it gives particular weight to those trees that are able to correctly classify points in the parameter space that are difficult to classify. And this is exactly what XGBoost, which is the approach that we used, does. The third challenge is how do we sample the parameter space? So what we do is to use an active learning approach where we basically try to ask the model to tell us what are in reality the parameters that produce a behavior which is close to the data iteratively in a way that our learning algorithm make the surrogate learning, especially on those areas of the parameter space where classification is particularly difficult. And this is done through the ex-ante specification of a budget. So the idea is that the user can specify a budget. The user more or less know how much time a given evaluation of the model costs in terms of time, and specify how many runs it is willing to perform in order to calibrate the model. And then this approach is tested across a variety of possible budgets. We present the results with respect to two models. The first one is a growth model, focusing on technological change and the interaction between firms. And the second one instead is an asset pricing model focused on the interaction between traders. In both models, you can see is that you save a lot computational time, and increasing the training samples, so the amount of ABM runs that you are willing to use, at some point, the gain in time that you have shrinks, but you keep increasing your precision. On the right-hand side, you see the mean square error that your prediction has. And even with a relatively high but not impossible number of simulations, what you find is that the mean square error is quite low, and it reaches 7%. And this is true for both models that we used. So we were able to, in the end, do this essentially. So this is the parameter space according to two relevant dimensions. The plus, they indicates the points, the positive calibration points, so the ones that satisfy our calibration criterion that are used to train the surrogate. And then you use the surrogate to predict this, the classification of this, of every point in the parameter space. And according to the certainty that we have that the point is a good point, we provide colors. So what we find is that there are areas where the model produces a behavior which, according to the ex-ante specified criterion, matches the empirical reality. Which surrogate to use? One of the common approaches in the literature was to use kriging, so Gaussian regressions. The downside of this is that it basically assumes a quite smooth response surface. What we try to do is to use an algorithm that is able to account for the often rugged response surface that we might have in ABMs, which is very typical in nonlinear models like ABM. And indeed, what we find is that the mean square error of our algorithm is way lower than the one obtained through kriging. Then what we did is to use the same approach for sensitivity analysis, and we again compared.
Sorry to interrupt.
Yeah.
Francesco, sorry to interrupt, but the time is basically gone 5 minutes ago. So if you can please.
I'm done.
Okay.
So the idea is that you can also perform sensitivity analysis, which is another very computationally dense process, quite efficiently, and you can also perform some comparative statics across the parameters in a quite efficient way. So to conclude, this is one of the area where machine learning has an added value in our attempt to provide friendly models. What I would suggest is to first assign range to the parameter space into relevant values where you know that introduce some estimation technique in order to find the actual best parameter value that you want to use in the calibration, and then you go back to the surrogate to perform sensitivity analysis in the surrounding of this point. So this will just to do with this approach. And sorry for taking more time than expected.
Yeah, no problem. Thank you very much. Next is Ernesto Carrella. I've seen here. So if you can please share your screen, and the floor is yours.
Can you guys see the slides? Then very quickly, let's go. What are we going to talk about? So very briefly, I think there is a better presentation coming by Matteo. I don't want to waste too much of his time. In fact, I should probably yield all of it, but just as a twisted sense of duty, I'll try to give a very quick introduction to what is, I think, a great contribution by him, just by providing context to what he is doing. So estimation, classic use of machine learning in agent-based models, really comes down, when you go to the technical details, there's many ways to do it, but they come down to 1 or 3 groups, right? One way, you set the parameters so they minimize the distance between the data and what comes out of your model, right? The other way to do it, you run the model many times, reject, you run it many times and you accept some runs, you reject some others. Finally, the third way, the more machine learning way, is, well, you can put parameters in the model will spit some data, try to learn how to go back from the data back to the model through regression. So for example, just to give an, so you could turn it into a triangle. You could say, well, something like rejection filtering, right, would be a rejection method. Something like likelihood methods would be a minimization method. And if you ever seen Radev's convolutional neural networks, a classic example of using, well, neural networks in that case, to get the parameters back, right? And meta models, although they use a lot of machine learning, right, like what we've seen just a moments ago, they tend to actually be minimization problems. They tend to be models about the distance function. I always suggest to start with approximate Bayesian computation. Bayesianism is a disease. It's a drug you should never do, not even once. But the literature itself is quite interesting, and it does span the whole gamut of methods. Mario is presenting after me. Produced a very nice paper on confidence sets. That's a rejection method. It's pretty interesting. And now he's doing something on lasso. I've done something on lasso, but it's just better. So, I mean, the only thing I wish is I waited a little bit before writing this, so my stuff will get cited a bit more. But besides that, it's really good stuff. And if Mario manages to do also a minimization thing, we can call this the Mario triangle, and then we're good to go. Now, the real problem it's about choosing the method right now that we have so many. And the real problem behind that is that you really have multiple objectives, and better methods are better for certain stuff. So the theoretical thing we want most of the time is consistency. That is, if we keep collating the data, will we eventually reach the true value for some definition of true? And there's less about techniques, it's more about choosing the right moments, the right kind of thing to compare yourself to. But eventually, it's a problem of indirect inference, ergodicity. There's a bunch of papers on this. It's really important in economics because in economics, parameters have deep meaning, right? You find out that people discount time at 4%, right? You write this in Econometrica. You can write all sorts of policy analysis out of it. But sometimes what we care about was what Francesco before mentioned a lot was efficiency. It's not, I don't really care that in the long run we get there. I want to run the model as little as possible to get some parameters. And that's probably where the minimizers tend to do better. But you pay a price for this. I'll show in a second. But in reality, there's no free lunch. I presented last time a bunch of examples of simulation, last social simulation conference, versus a bunch of algorithms. I could always find one problem or one of the algorithms was better than the other. So that stuff there's rarely a winner in the efficiency game. But there is sometimes where you don't know how the distance function should be or what moments you should focus on, and regressions tend to be good for that kind of stuff, which I think is what Mario will focus on next. So if you care about point estimates, these are the 3 things you tend to care about. But sometimes you don't care about points themselves, you care about confidence intervals around parameters. And some methods do it better than others. Sensitivity analysis is important, right? How much should I vary the parameters from what I calibrated? If you don't have confidence intervals, it's very arbitrary. That's not usually very good. Bayesian methods, right? Unfortunately, the advantage they have is that they always produce a posterior, if you're willing to believe it, of course, and that can guide you into what are you certain about, what are you not, right? So that's useful, but that's something that rejection methods do really well. Confidence intervals, Bayesian and non-Bayesian, and some regression methods. Lassos tend not to do this very well. But prediction intervals can be turned into confidence intervals. Now, yesterday we learned that we're supposed to call this inverse generative social science. Sometimes it's not that we care about the value of the parameter or the confidence interval around the parameters. What we care about is we want a set of valid parameters. That is, parameterization A, parameterization B will work. They're both generators, as they called them yesterday. And this is still an estimation problem, as long as you're willing to. Yesterday they were using genetic algorithms, genetic programming, but really that's a non-parametric version of just accepting multiple stuff, picking a bunch of parameters. And rejection methods do that very well. Now, in fact, you can also do it by genetic algorithms. You can do that prediction intervals. The real problem, the real something that was not brought up yesterday, but it's important, is this is useful as long as you can put likelihoods on the scenarios. If you produce 100 scenarios and you tell me, oh, this is more likely than the other, or you tell me, and I believe you, these are all equally likely, that's great. We are in central limit theorem town, we'll be fine. But otherwise, it's sort of useless. So, and rejection methods do that. So rejection methods do give you likelihoods on it. And last slide, we want identification, right? Most of the time, most of the models you use, it's not true that you can actually go back from the data to the parameters. And you're lying to yourself by just setting a parameter. The only way to figure this out is by doing cross-validation. So you have to run them, you have to create fake data and then run the calibration estimation methods and find it back. And that's where the maximizers do worse, right? Maximizers, very easy to get the spot, but then if you want to cross-validate, you have to redo that exercise many times. Rejection methods, regression methods is effortless. You just have to rerun the regression at worst, or you just split the data. So this is all I wanted to say. This is kind of the constraints and the objectives you're going through when you're doing estimation. I really like the lasso stuff that Mario's doing, and I think we should leave the floor to him.
All right, thank you very much, Ernesto. So very interesting. I'm totally new to ML, and Mario, the floor is yours. 10 minutes, yep, as agreed.
Okay, thanks. Many thanks. I will share the screen. Just give me a moment. Okay, so share screen. Okay. Where is? Okay, so this one share. Okay, just a moment. Right.
Yeah, no problem.
Okay. References. Chrome. Okay.
Ernesto has built expectations so high that we must see your presentation. There's no
share screen. Okay. Share. Okay. Can you see the slides now?
Yes. Yes.
Yes.
Okay. Now, can you see the slide?
I see them half only.
Yeah, it's half cut now.
Cut in half.
Okay. Just a moment. Okay.
Maybe if you just enlarge this.
Yeah.
Otherwise, oh no, they're off.
They're off. Oh, okay. Okay. Share.
Well, they're still cut a little bit. Maybe if you visualize them the other way, I mean, they are small, but I guess we can see something. So
I don't know. Now?
Slightly better, almost every. Yeah, now we can see them.
Okay, great. Great. Sorry for the inconvenience. So, first of all, I would like to thank all the organizers of this workshop for giving me the opportunity to present my work. And also, I would like to thank all the presenters and the participants. And thanks to Ernesto for this amazing presentation of my work. I would just like to give some hint about new estimation methods that we developed for the estimation of the parameters of the simulation models and also, of course, agent-based models. Our estimation methods is based on non-parametric regularized regression, which is also lasso regression. Is a generalization of the work of Ernesto and co-authors. And as I will show later in the presentation, I will just introduce our estimation methods. Then I will go through the asymptotic properties of the estimator briefly. And then I will show an example just to show you the final sample properties of the estimators. It's a bit more technical than the other presentation, but I try to simplify my presentation. Okay, so the motivation. Why we decide to consider lasso regression instead of more classical estimation methods. There are some motivation for this. First of all, because classical estimation methods, among these we can recognize indirect inference, method of simulated moments, method of simulated minimum distance, approximate likelihood, approximate Bayesian computation, and so on, are very expensive in terms of computational time. If you consider some estimation methods, you have two choices: a statistical metric to measure the dissimilarity between simulated and real benchmark observation. And of course, you have to identify the moments to match, basically. For instance, in indirect inference and method of simulated moments. Another very important point, and I don't have too much time to explain here. Maybe later in the discussion we can discuss about is the ruggedness of the objective function. What do we mean briefly? If you consider classical estimation methods, you have the objective function and you have to optimize an objective function, right? So this objective function in ABM is not smooth enough, which means that you cannot identify the true parameters. You're not sure that this parameters is the true one. So because of the ruggedness of the objective function. And this is a real problem, which is recognized by some authors. Among these, we identify Gill and Winker, and so on. This led to multiple local minimum and to ad hoc algorithms to provide for the optimization of the objective function. As I said, our goal is to find the parameters that produce the statistics that are close to the ones obtained in real benchmark data. What does it mean? It means that, as I explained in the next slide, basically, we want to estimate a parameter using as a regressor the statistics. Okay. Why did we decide to choose lasso non-parametric regression? There are some motivation. Some of that there are shared with the one explained by Ernesto, of course, because it's less computational intensive than the other methods based on optimization. Because it's flexible, as it depends on the parameters on the statistics, it's non-parametric. This is specifically for our estimation methods, as we consider non-parametric estimation instead of parametric estimation. So we're not based on any function, density function, for instance, some that. The joint estimation and automatic selection of a subset of basis function. I will explain later what are basis function used to model a non-parametric dependence. Of course, the estimation of each parameters can be made separately, and this leads to a reduction in terms of curse of dimensionality, if you think about the parameter space. because it's applicable in the same way to both time series and independent replication, which is really important, I think. And because, of course, one of the most important, I think, is that no continuity condition of the objective function are required to prove the asymptotic properties of the estimator, because it's not based on any optimization, and we are not thinking about the continuity condition. Of course, we are not characterize the central limit theorem. We are just only characterize the convergence of the parameters of the estimates to the true parameters, as I show later. Okay, so just in a few words, our technique, as I said, is a generalization of the method of Carrella. We had sieve estimation. I will show in the next slide what we mean with the estimation. This is our setup, and we characterize also the asymptotic properties. So this is our setup. We consider simulation models indexed by vector parameters. It's okay. We have for n parameters value in the capital theta, which is the parameter space. We simulate one or more runs used to compute m, which is greater than k statistics. So m is the number of statistics, which is greater than the number of the parameters. And we estimate a Lasso non-parametric regression of this form, where FP is an approximation, is a linear approximation of basis function. And of course, as a regressor, we consider the statistics. So basically, this is the construction of the function FP. Imagine that we want to estimate a parameter theta, taking the case of two statistics. These two statistics could be the mean and then central variance, for instance. We build a vector of monomials. Now we consider monomials, which is the power of the statistic, but we consider also, for instance, orthogonals, polynomials, and so on. We build the vector of monomials S1 and S2, and we take the set of all possible interaction, which is the tensor product or Kronecker product, and we build the function in this way, basically. We have beta 1 times 1, which is the first parameter, and beta 1 S1, and so on, which is the set of all interaction. Okay, so here I just want to give you an idea on the bound that we found for the asymptotic convergence, which is, of course, the error in the estimates of the parameter, which is basically depends on tau, which is the regularization parameter of the Lasso regression, and depends also, the asymptotic parameters are S, which are the number of observation, R, the number of simulation, and the number of parameters values selected in the parameter space, and P, the number of items in the dictionary, basically the polynomials that you consider to track your function. Okay, so just to give you some hint about the simulation experiment, we consider two cases. One consider the estimation of a parametric function of the statistics, and another one which consider a non-parametric function of the statistics. For the first case, we consider the estimation of the mean of the Gaussian random variable, and for the non-parametric case, we consider the estimation of the standard deviation of the Gaussian random variable. These are the results. This is the bias of the estimator. These are the variance of the estimator of mu. And these are the results for the estimation of the standard deviation. As you can see, just to conclude, here we characterize the asymptotic rate of convergence of our parameter, which is, of course, suboptimal as compared to parametric case, but the loss of efficiency in terms of convergence rate is compensated by the flexibility deriving by the non-parametric estimation of the function. And finally, the result of the simulation is just a trivial example of is a first simulation. We have that when the parameter to estimate is a parametric function, as in the case of mu, we have the bias is negligible and tends to decrease when S, R, and N increase. when the parameters to estimate is a non-parametric function, we have the bias seems to decrease, of course, but is not directly interpretable nor negligible. And in both cases, the variance seems to reach the Cramer-Rao lower bound, which is the level with the minimum variance of the estimator. The estimator seems to be efficient. That's all. Thanks.
All right. Thank you very much. Thank you very much. We have still some time for comments or questions before we all go to listen to Josh Epstein in the keynote from 6 to 7. So the floor is open. Either raise your hand or unlock your mic if you want to say something.
Yeah, I have just some consideration about the use of machine learning in general, and also the use of machine learning in ABM and simulation models in general. I think that in the presentation of Matthias, he said that sometimes machine learning is used because it's popular as a technique, but I think that we have to think when it's useful to use machine learning instead of the more classical statistical techniques. Of course, for instance, you can think to use machine learning when you have to manage and to dealing with a large amount of data. But in our case, agent-based model can be considered as big data, are a large amount of data or not.
So do you want me to comment on this?
Yeah, no, it's just a consideration, just to open to the floor.
I actually agree. We have to ask ourselves, when is it useful? And we saw, for example, the application through the reinforcement learning, and I don't know of any other method capable of having this flexible behavior in agents. But when it comes, for example, to building classes or clusters of data, then of course there are many other possible ways to do that. And I don't know of any particular paper which actually analyzed what is better, traditional statistics or machine learning. As I said, most of the papers have a proof of concept character, just stating it is possible.
Yeah.
Just a small comment then on machine learning in terms of to simulate the behavior of the agent, right? So reinforcement learning, but it could have been something else, right? And I guess we go back to bounded rationality from the presentations before, and even before, on the importance between environment and the agent, right? Or we make the agent complex, but the environment is simple, right? And I think the problem with reinforcement learning, it covers the ones before, is really about proportions, right? So, okay, if I have a very complicated agent dealing with a very simple environment, it looks strange. And if I have a very complicated environment, a very dumb agent, then it also looks strange. And reinforcement learning, I mean, if you code it right, if you train it enough, it's probably gonna go almost superhuman level, right? And that's not necessarily what we want, especially if we think there is some bounded rationality. So I guess the fear I have of that, although it's something I really want to explore, and I'm happy you guys are doing it, is really the tool, it's sort of escaping the purpose for which the modeler put it in, which is not necessarily a good thing.
Yeah.
Actually, you referred to an important point. Machine learning is often considered as a black box, and you can put it this way: in many applications, you have a black box which is called ABM, which you don't understand correctly, and you try now to make a second black box in order to help you to answer questions about the first black box. And this is an endless loop, maybe, particularly when it comes to agent behavior. Yes, you're right. We should ask the question: what is the purpose of doing that? But here again, you make you open some black boxes, many black boxes, maybe with connections, and this is indeed a problem. But still, it opens up something completely new, and this is this absolutely dynamic and flexible behavior of agents. And although this might not be true for human beings, I think it's worth considering and exploring, but just as you said.
Yeah, I think that's the point. I mean, in terms of black box, because it depends on what you want as a result. If you don't care about the asymptotic properties of the estimation, so you can go for machine learning techniques, for instance. But I think that you have to think very much what you want to do. So basically, do you need machine learning? Do you need more statistical techniques? So that's true. That's true.
Just to comment on this, if I can, I just turned my video off because my connection is not very good. I think modeling the behavior of agents through machine learning techniques to machine learning algorithms is very risky. I think in order to model behavior, we should stick to the empirical evidence and the evidence that we get from the analysis of the management literature for firms, psychology literature for other kind of individual behaviors and this kind of stuff. What instead I think would be very interesting is to use machine learning techniques to let policymakers in the model learn. So for example, I would like to have in my model that the central banker, it can learn through some technique and adapt the policy through the state of the economy that might be in different regimes. And so I can feed, in principle, these agents with the whole information of the simulation model and allow the policymakers to learn and to optimize the policy. Because in many cases, at least in my literature, in the macro ABM literature, policy testing is very simple. So for example, we assume that the central bank follow a certain Taylor rule for the interest rate, or we assume a given tax schedule, and then we change the tax schedule and we see whether there is a difference. But it's very complicated to end up with dynamically adjusting policies that reflect policy changes where the behavior of the economy change. This is something that, at least in my literature, is something I've not seen. Mm-hmm. And I also fear a lot the explainability of machine learning techniques. For example, in my application, in the end, I used decision trees and forests because they have good performances, but still you can a little bit understand how they work, and at least you can rank features, you can rank parameters in terms of their importance in driving the behavior of the model. I tried with the neural network, the prediction performances, they are much better, but I cannot understand what's happening in the model. So I think we should also try to take this trade-off into account.
Right.
Maybe 2 points on that. So first of all, the micro surrogates or employing reinforcement learning to model agent behavior. So I agree, it depends on what you want to do. If you want to have a really realistic ABM, then it may be risky to do so. If you take on a more normative stance and try to figure out, okay, what is the optimal strategy here, then it might be more useful, because you can, for example, implement a central planning agent, equip it with reinforcement learning, or have coordinated reinforcement learning between the agents. And then a second thing on the value of machine learning, maybe as a more simple tool to also use, being used by modelers that are not really that deep into machine learning as you guys maybe are, is the analysis of the output data, right? Where you can simply use the output data of an ABM, which is arguably big data, hard to analyze for some macroeconomic ABMs simply through playing around with the parameters in a dashboard. And then you can, for example, try to find clusters of scenarios in the data And then, as Francesco said, use a tree-based algorithm that is easy to trace back which kind of parameters lead up to these kind of clusters of scenarios. So maybe deriving some narratives from the output data of an ABM a bit quicker, maybe, especially for large scale ABMs.
I personally agree.
Yeah, me too.
All right. Well, thanks everyone. I think it's perhaps time that we stop, because as I said, there is a keynote lecture from Josh Epstein. I'm sure most of us would want to listen to. It starts at 6 o'clock, so we have only 3 minutes, and I would like to take 1 minute to say thank you to everybody for a really interesting presentation. I had lots of fun. I learned a lot. So I think we had a pretty good variety of different thoughts on various combinations of ABMs and their boundaries. So perhaps we have a relatively clear idea of what it is. So with Raffaello and Mario, we've been discussing a little bit about a possible special issue. We don't have an idea of where to go about it, but I just wanted to let you know that we're thinking about it, and if things progress in a certain way, for sure we'll let you know, and we will invite you to elaborate on your recording, because everything is recorded here. So, but again, thank you very much, everybody. It has been a great afternoon and evening, and I guess I'll be seeing you on the other Zoom room. All right. Bye-bye. Thanks.
Bye. Bye-bye.
Thanks.
Bye.
Thank you, Davide.
Bye.
Thank you very much to the organizer.
Thanks.